Yeah, your screen is visible.
Yeah, thanks. So, hi teams. Welcome for this virtual dynamic event webinar for the BAJA India 2025 season. My name is Harish, and today we will be going through the virtual dynamic training for the new season. So, we will also going through the new format that we are introducing for this year. So, before we start, let me just go through the schedule that we had posted on the Instagram. So this was the schedule that we had. So to show you a very detailed training session that we will follow is first we'll start with the overview of the software, which will be presented to us by IPG team. And then I'll give an introduction to the new VDE format that we will be following. And we will then cover the moment of inertia and the kinematics in IPG CarMaker. And then we'll have a short break, and then we will go through the different virtual dynamic scenarios. And then at the end, we will have a session from MATLAB and co-simulation with MATLAB. And then at the end, we will have a Q&A session. Now, to begin with the first session of the day, we have here Mr. Avinash, Mr. Jignesh, and Mr. Adesh from IPG Automotive India, who are the solution engineers and are here today to talk about the software and its different functionalities, and also give a small introduction about the CarMaker software as well. So, Avinash, please take this forward. Now I pass the mic to you.
Thank you, Harish. Good morning, everyone. Thank you for being here today. I will share my screen for the presentation. Is my screen visible to everyone?
Yes, yes, it is.
Okay. So at IPG Automotive, we are developing a pioneering simulation solution software and hardware for the virtual vehicle development. So the IPG Automotive founded as in 1984 as a spin-off from Karlsruhe Institute of Technology. So initially it was more focused on vehicle dynamics and hills simulations. So we have around 40 years of experience in supporting our customer with the solution for virtual test driving. And we have invested over 20 plus years in ADAS and autonomous functions. So in our company, we have around 400 plus employees globally, and it's growing rapidly. We have 16 plus offices all over the world, and 250 plus companies use our software. So we offer virtual test driving as a solution, and it will help the customer to develop uh, like as a pioneers for virtual test driving. We are constantly has been expanding our expertise from 1984, and we understand the our problems of our customers, and we are giving the solutions for ADAS, powertrain, and vehicle dynamics, autonomous vehicle, etc. So our simulation solutions and test systems help customer to increasing the development requirement in automotive industry and for individual use cases. The method we use is based on automotive systems engineering approach, which is characterized by development and testing of complete systems, like every part of the vehicle. So, and virtual test driving, we put this approach into practice with the full vehicle as well as with the realistic test scenarios. is that we are number one in virtual test driving in all our application areas. So I can skip this. Like uh, we have every like in our software solution, every engineer has the opportunity to evaluate the new systems in the full cycle at each development cycle. So one of the application area is autonomous vehicle, and like our software provides the perception and localization, motion control, decision making, and motion planning, and full system validation through our software we can do. What are the benefits of this? Our software will give complete simulation environment from a single source. So we can use the motor, sensor models, vehicle, and environment simulations. So, and one more thing is that you can every time you can reproduce the same and different scenarios, and you will have the flexibility of using different. It is compatible with different Assam standards, and the physical validity, tried and true vehicle dynamics, and sensor models with various levels of complexity. The flexibility in applications and efficiency and scalability. So Jignesh will continue this. Jignesh, can you share your screen?
Hello,
Jignesh.
hello.
Yeah,
Yes, you are
you can.
Uh,
audible.
okay, sure. Is the screen visible?
Yes, yeah.
Okay. So we provide solutions for ADAS creation. ADAS, if a customer has a certain requirement for ADAS, we provide the solutions for that. So let's say if there is something a customer has very specific for his requirement. So in CarMaker, we provide the solutions for the ADAS features from level 0 to level 3 plus. So with this, the use case can be said, the customer can validate his active safety system plus NCAP with V2X communication, and also can do the comfort system testing. So as Avinash said, it's a comprehensive simulation system or the software where a user can build his own roads, his own scenarios, where he can model his own vehicle. Plus, he can even add certain features such as ADAS functions to his own model. With that, even in case a customer needs to do a higher testing on it, he can also integrate his particular models to the real-time systems with and it also can be connected to the test benches for different applications. So so yes, so basically the software can be easily integrated with different components to achieve different uh, outputs or the reports of, with respect to that particular standard or a use case. So with the vehicle modeling part, we provide a powertrain setup where you can a user can build his own model where he can integrate electronic defined powertrain system, a smart connected powertrain system. So again, once the you have a flexibility or a capability to integrate it with the real-time system and test those features with like in a loop with CarMaker software where you can visualize the things with respect to the real time as well as in CarMaker visualizer. So yeah, uh, when you can when you have some certain requirements with respect to vehicle dynamics. So with this software, you can program or parameterize your steering system, where you can develop a certain type of steering system, chassis control system, and you can even develop a suspension design, which all can be real-time compactable, where with the vehicle dynamics part, you can give certain loads to the chassis, or you can even parameterize the uh, positioning of the components and even the weight to it. So I think Adesh can take over.
Yeah, sure. So let me know once the screen is visible. So is my screen visible?
Sadesh. Yes, it
Sorry.
is visible.
Yeah, let's start. So when it comes to the V-cycle development for the virtual test driving, so requirements such as model in the loop or software in the loop, it can be easily achieved through car maker software. So you can also for the real-time systems such as real-time computations, use cases such as hardware in the loop or the vehicle in the loop, we provide an interface called as XPAC4, which is integrated along with the car maker. So this is the solution we provide for the virtual test driving when it comes to the V-cycle development of the cars. Moving to the next slide. Just give a minute. So yeah, as they mentioned before earlier, areas of application, namely autonomous vehicles, ADAS, powertrain, vehicle dynamics. So these are the major areas we focus on, and we have our expertise. Not only these areas, not only these areas, but also beyond this, we can provide the solutions. So CarMaker software works on a closed loop simulation. So when it comes to virtual vehicle prototype, it's a closed loop simulation where in the closed loop simulation, it's a inclusion of roads and infrastructure, driver model, and the traffic and the environment. Also, the specific subsystems and the models or the components can be integrated very easily. So, the roads and infrastructure, for example, we can input the map data and also the road measurement. Also, we can edit those measurement or the map data using the scenario editors. So, when it comes to IPG driver, we have a set of IPG driver model which have adaptations, and also driver in the loop can be integrated for some use cases are the autonomous controls, then the traffic environments, road recordings, and traffic simulations can be edited through the scenario editors. So the car maker product family. So under simulation software, we have three products under simulation software for different vehicle class, namely car maker, truck maker, and motorcycle. As the name suggests, car maker for the car, and a truck maker for the truck, and the motorcycle maker for the motorcycles. So the structure between these three are the same. So CarMaker is a virtual test driving software. Like you can do the virtual test driving. It's a closed loop simulation. Along with that, we provide it's compatible with the integration platforms. For example, if you have a models, let's take a model of Simulink. It can be easily integrated along with the CarMaker. Also, when it comes to the visualization of the simulation, we provide a platforms such as instrument designers and IPG movie and movie NX, where you can easily visualize your scenarios you built. So the next compatible thing along with CarMaker is test automation and evaluation. For example, if you have 1,000 test runs and you need to do it overnight, also you need to generate the report. It can be done using test automation available in CarMaker. So then the scalability, HPC, and the cloud. So CarMaker can be run in a headless mode, and also it's compatible with AWS. You can create your own Docker. More like a cloud computing is possible through CarMaker. So this is one of the visualization I was talking about. This is the example for a movie NX. So it gives a photorealistic visualization of your simulation, and also it uses the real physics and a strong graphics. As you can all see the slide, it's bit on a more realistic sides. So when it comes to products and services, we have gone through simulation software. It is nothing but car maker, truck maker, and motorcycle maker. Then the real-time hardware, which is the uh, XPAC 4. Then the test benches, what here it's mentioned, it's nothing but a steering and test bench. We also offer engineering services. So yeah, this is one of the examples for vehicle in the loop. So this is the vehicle in the loop we have created, the real world vehicle in the loop demo vehicle. So then this is a comparison between the real world versus the virtual world. So yeah, that's about brief about IPG. Thank you.
Hi, Harish. Can you take on from now?
Yeah. Thank you, IPG team. Thank you, Avinash. Thank you, Jignesh and Mr. Adesh. I hope this had given a very brief introduction to the Karmika software to all the teams. Now, let's move on to the most exciting part of the day. I'll just share my screen. Yeah. So I hope my screen is visible. Can someone just confirm that?
Yes, you should.
Yeah, thanks. So as we are done with the first session of the day, now let's begin with the second one, which is the introduction to the new VDE format that I am sure all of you would be very excited to hear about. So before I talk about the new format, so let's just go through the old format that we were following for the past 3 seasons, 3 to 4 seasons. So the first is the vehicle parameterization. So all teams would have to build their own model with the design parameters and values that they have selected for the vehicle design. And then after modeling the vehicle, BAJA SAEINDIA would release the virtual dynamic event tracks such as Manu and ATP. And you as team would have to parameterize and give the maneuver, do the maneuver parameterizations. So from the start to end, the driver models and the speed and the lateral dynamics, everything would be defined by the teams so that they achieve the best lap time and then submit that test run for evaluation. Now, for this new season of BAJA SAEINDIA 2025, we are changing that format, especially in the phase 2. So there you go. This is the new format that we will be following. So in phase 2 particularly, so we will be having a VDE static presentation round along with the VDE simulation round. So the phase 3, which is a validation event, will be the same. So our main focus and the change in the format is in the phase 2. So in the phase 2, the VDE static or the VDE presentation round is basically introduced to evaluate the virtual validation process of the BAJA vehicle that the teams are following, and for 5 different virtual dynamic scenarios. And teams have to simulate their vehicle for 5 virtual dynamic scenarios, which of course we are going to talk about in very detail in our following sessions. And also I'll also mention what are the different 5 virtual dynamic scenarios in my next slide as well. So teams have to optimize their vehicle performance and understand how their vehicle is behaving and optimize their vehicle using these 5 virtual dynamic scenarios. And the final model that you will be using, the final model, optimized model, is what you will be using for doing the lap time simulation in the VDE simulation round. Now, the VDE simulation round, so there is also a slight change in that. So till last year, we used to have 2 virtual dynamic scenarios, Manu and ATP, as I mentioned before. But for this season, we will only have the ATP round, all-terrain performance track. So, and another change is that the maneuver parameterization. So the maneuver commands will also be given by us, the BAJA SAEINDIA, to the teams, which will be common for all the teams. So from the start to the end, the maneuvers that you have to give has to be strictly followed as per what will be released in the guidelines later for the virtual dynamic event guidelines, VDE1 and VDE2, which will be released soon as well. And the VDE presentation round guidelines will also be released, which is scheduled to release soon as well. And the scoring format and all other guidelines, rules and regulations will be mentioned in the guidelines specifically. And teams have to follow the scenario and the maneuvers which are defined in the VDE presentation round guidelines as well for doing the simulations at their end. And then the results that you are getting is what you have to talk about in your presentations and have to explain it to the judges in the static round. Now, as you can see that the teams will be evaluated based on both the presentation round and the ATP. So teams have to compulsorily attend both presentation round and the simulation round. Now, let's move on to the different virtual dynamic scenarios that I've been talking about. So the virtual dynamic scenarios are 5 virtual dynamic scenarios for this year, so which is acceleration, brake, constant radius, on center, and step steer. So in the detailed schedule that I showed previously, there were sessions regarding each virtual dynamic simulations, which of course we will be going through after our break on the second session. Second part of the session. So these 5 scenarios will be common for all the teams, and teams are open to explore more scenarios and include them in their presentations. And what all has to be included in your presentation will be mentioned in your static presentation round guidelines. So to give you a basic idea of the flow that we will be following is that the VD presentation round guidelines will be released, and this will be common for all the 3 event categories, MBAHA, EBAHA, and HBAHA. So, and the ATP track will also be released as well after, along with the VD guidelines 1 and VD guidelines 2. The dates, the deadlines, everything will be mentioned in the guidelines. And you would have to do the static presentation round, and you will be submitting your ATP test run in which you are getting the lap time that for evaluation of the simulation round. Okay. Now, before we begin with the next session, let me just give a small intro. So, of course, you have all received your licenses, and you would have started working with the CarMaker software, and also we have released the self-paced course on the forum. So I hope you guys would have gone through it, which will give you a brief introduction to building a vehicle model. And also the CarMaker guidelines has been released for M and E BAHA. So you can refer to that of the 2025 season. And for the HBAHA teams, you can refer to the previous 2024 CarMaker guidelines. So the 2025 season new CarMaker guidelines will also be released soon. The first thing that you see in that CarMaker guidelines before beginning is that the project workspace creation. So even if you are building your own, you have started working, you have created your project folders, but for submissions is what I'm going to show you. So you can just go to the main GUI, you can go to file, and you can go to project folder and create project. So in the create project section, you can just type in the name team ID _ team name. Okay. And just make sure that you select all option you selected and you just press OK. So your project folder in the name of team ID _ team name will be created. So this project folder is what you would have to submit for your VD simulation round. As per last year as well. So that will also be mentioned in the VD guidelines 1, which will be released soon. Now, so I'll just show you. Sorry. Yeah. So this is the project folder that I have already created. So I have renamed it to team ID _ team name. Now, if you go to data and let's say vehicle. So I'll have my team ID _ team name _ vehicle. So the naming convention and the format that you have to follow is also mentioned in the CarMaker guidelines, and you have to strictly follow that. So similarly goes for your test runs. You will have your test run team ID underscore team name underscore test run, and inside which you will be storing your test run for ATP, and then similarly goes for your SKC files if you have any. So if you have a SKC you have created for both front and rear, or if you have only created for the front, you will create a separate folder and then you will save it in that. So this has to be strictly followed, and this is how you have to compress this whole project folder, team ID underscore team name, and then you have to submit it for evaluation. And yeah, so now moving to the software. Sorry. Yeah, so after you're done with your project folder creation, so I'll just quickly go through the yeah, so I'll just quickly go through the vehicle dataset. So as I mentioned before, we have released the self-paced courses. So you can go through the self-paced course. You can understand how to build your vehicle model. So each parameter that is required. So let's say, for example, you need the most important parameter that you would need is the moment of inertia, the mass values, and these positions. So these positions basically define your track width and the wheelbase. And this moment mass of inertia is or the moment of inertia is crucial for the vehicle. So we are having another session regarding that as well. So you will understand how to get that from any CAD software, or how to input those values. And then let's say in terms of suspension design, right? So you will be using a kinematics or a linear DOF model, or you can use a SKC file or an MBS. But it is recommended for the teams to use a SKC file for the simulation round and for the presentation round, or else you can use a DF model as well. But we are also having a kinematics session, a detailed session. So you will understand how to build your own SKC files. So I'm sure it will clear out all the doubts that you would be having in terms of making an SKC file. And then similarly, we have the steering, brakes, and powertrain subsystem. So powertrain for MBAHA, you can use the conventional, and for the EBAHA, you can have the electrical powertrain, and you can define your all the values that you have for each parameters. And now another major thing is the inertia values. Everywhere the inertia value is getting asked, so it is important. And now moving to the main assembly folder. So at the bottom, you can see the info file. So this info is very important because it gives you an overall picture of the basic information of the vehicle. So let's say you will have the overall mass, and then the inertia tensor and center of gravity position and the inertia tensor. So what this inertia tensor means, and the understanding behind this, I'll cover that in the following virtual dynamic session when talking about it. And then you have other basic parameters as well, so which basically defines the physical characteristics of the vehicle, and which are very important and gives a basic idea of how the vehicle will behave in a particular scenario, or in a particular dynamic scenario. So these are some informations that you can also include in your presentations. So which will also be mentioned in the guidelines, and which is scheduled to be released soon. Okay, so now with a small intro of the car maker software. So also in the help section, you will have, I'm sure you are aware of the reference manuals and the user guides and the product examples as well. So let's say in the reference manual, the main important stuff that you must understand is the yeah. So in the reference manual, you have something called as a UAQ. So UAQ is the user accessible quantity. So for each subsystem, let's say we go to just a minute. Yeah. So let's say just we go to car. Okay. Yeah. So Yeah, so let's say we are in this section of car, right? So we have different parameters, car.ax, ay, az, so which are basically the acceleration, translational acceleration values. Or with respect to time, it will basically give you the instantaneous acceleration value. So we will be going through these characteristic values, and which basically defines the vehicle behavior, the car.v, which gives you the velocity, and then you have other parameters as well, which you can map or plot in IPG control, and then understand the behavior of the vehicle. So to give you a short intro of IPG control, so you can go to file and then you can just press on IPG control. So okay, so yeah, so here you can see this is the graph, or the main window where you will have the graph will be plotted, and then you will be having the quantities listed out here. So as I have not started any simulation, so no data has been loaded. So if I do a simple simulation, okay, so let's say I'll just take a product example. Okay. Okay, so I've just taken a product example just to show you. Now, if I just run it, yeah, so everything has been loaded, and this green button that you, or the green shape that you're looking is basically showing that it is online, and it is recording the data. And also you can, in live, you can plot the value. So let's say in the car, I want the AX, okay, the acceleration value. So I can just select this option, and yeah, so I can just select this option, and this will start plotting my graph. So I can just, yeah, so as you could see, my graph has been plotted, and I'm able to see the behavior of the instantaneous acceleration of the vehicle for a set course of, or the stretch of road. And yeah, so in this also you can also select the unit. Let's say you are looking into car.v. Okay, so initially by default the car.v is in meter per second unit. So if you want to yeah, so if you want to change the unit to kilometer per hour, you can do it from here. And it will show you the results in kilometer per hour. You can get an idea of what speed the vehicle is moving. And at the top, we have few options like file, you can add another connection, or diagram, you can add another diagram at the bottom. You can parallelly view more graphs here. And then at the settings, you can set the sampling rate and other color maps as well. So you can also change the color for this. Let's say you want to display it for some other color, red, dark blue, or you want it to be undisplayed. You can just click on that and it will just move out of the window. Now at the top you have the y-axis, so you can set what value you want for the y-axis. So by default it is always the time at the x, but let's say you want to have a graph between steering wheel angle and lateral acceleration, or yaw rate versus lateral acceleration. So you can plot that graph and understand the behavior of the vehicle. And then let's say I have plotted this. Just a minute. So let me just start again. Okay, so yeah, okay, so I've completed the simulation. So let's say I have this graph. Now I want to know what is the maximum value. Okay, so what I can just do is press shift and then left mouse button, and you just have to drag it. Okay, so once you drag it, and if you select, you can see that the area is highlighted. So let's say I just select on the graph, so it will give me the maximum value. So this green value is the maximum, and if it comes in red, so here you can see it is in red. So this is the minimum value. So it gives me both the x and y. So let's say the kilometer is minimum I'm having is 8.75 kilometer per hour, speed, and the maximum is 72, right? So this is how I can understand what is at the maximum value, or at some average value also I can get. So I can set that in this cursor, in this preset, sorry, not here. Yeah, in this cursor. So this option at the top, I can set what value I want to see. I want to see min max or delta or falling edges or integral or sampling points, etc., etc. Okay, and moving forward, so as I said before, you can, if you want to change the x value, you can just press on the x, and you can change what you want at the x-axis. And then you also have, if you just right click on the main window, so you have options like totally fit. So let's say when you are doing a simulation and it's running in live, so what would happen is you might zoom in or zoom out, right? So you can just fit totally to see the overall behavior of that particular characteristic value. And then you have other options as well to delete the diagram from here, or add legends or show it. And also you can export the data that you are having. So you can export it to a file, let's say Excel file. So we will be showing you how to export it and then doing post processing as well. That will be covered in the sessions for the virtual dynamic scenarios. And then you can also print it. So let's say you want to print this graph, you can just give, let's say, car dot vehicle velocity, speed versus time. Now I just give this, I keep the layout as default. I want to know the grid as well. So I want to know like at what instant of time I'm having what velocity. So I can just turn the grid on. I can keep the full width of the axis, and I can just hit on the print option. So I'll get the graph like something like this, and I can just then export this data, and then maybe you can paste that same data in your presentations as well. Also, so another thing that is very common with IPG control is, I'll just show you the movie as well. So you can basically track how your vehicle is behaving, or you can just sync IPG control and the movie. So let's say I have this scenario built. So this is called as the virtual scenario that you have, which you are building in the scenario editor, and you are running it in the movie, right? So let me just start. Sorry, yeah, so it's starting. Yeah, so it is starting now. And yeah, so the simulation is over. So at the corner, if you just drag it a bit and, pan it, so you can see as this sync option. So if I just move this, okay, so this is moving, right? So if I just keep it side by side, and if I just move this, you can see the movie is also moving. The slider in the movie is also moving. So let's say at this instant, right, at around 8 to 11 seconds or 11.5 maybe, my velocity is 69.7, right? So it's around 69.70. And if I go to this position, right, so my movie is also moving. So right now this is a very plain scenario where the vehicle is just moving straight. But let's say you are simulating it under a way, different bumps, how your vehicle is performing, or how your wheels are traveling, or because of some external force, if your wheel is the travel is more or it is less, to understand the whole behavior of the vehicle pictorially, or visually, you can do this. It's a very good feature with that. So yeah, so that's all from my side. So and in the first session, thank you so much, IPG team. And also I hope you have got a bit of gist of the new season that we will be following for this year. And yeah, so we'll now start with the third session of the day, which is regarding IPG coordinate system and moment of inertia. Yeah. So Rhythm, are you there?
Yes, we can.
Yeah, let me just stop sharing my screen.
My screen is visible, correct?
Yeah, it's visible now. Yeah, you can start.
So hello teams. So hope you were going with the new format of the IPG basic. So the basic maneuver you will be applying is for the optimization of your vehicle. Starting with the first, we will need to apply a car file for each and every maneuver, which defines your specific car, representing your BAHA vehicle. So for each and every car parameters, you will be having some sort of mass. Every component has some mass and their specific moment of inertia. To go with this moment of inertia, you will be required a specific value which you can calculate with the help of CAD software. For each and every parameters such as the chassis, powertrains, and other trim loads, you can enter your specific moment of inertia. So for each and every parameter definitions, you can refer the reference manual and user guides for your reference. Starting with the first, how, how the moment of inertia works. The definition of moment of inertia is as the moment of inertia of a rigid body about an axis of the axis is defined as the sum of product of each unit masses and square of its perpendicular distance from the axis of rotation. As you all know about this definition, the formula is pretty simple: mass into square of distance. This distance is referred from a specific axis of rotation. To come up with this specific axis, we will require a coordinate system. This coordinate system is at the FR1 coordinate system for our IPG car method. So, what is FR1 coordinate system? To refer this coordinate system, you can go for the reference manual in the section 1.2 car maker axis system. You will have a look at the different coordinate systems. So, coming to the FR1 coordinate system, it is located at the rearmost point of the vehicle. Yeah, here is a summary of the FR1 coordinate system, that it is located at the rearmost point of the vehicle, as well as the directions are as X direction moving forward in the driving direction, whereas at the left we are having Y, and in the upward direction we will be having Z. By applying this coordinate system in our vehicle's CAD model, we can generate a moment of inertia value. So, at very first, you will be requiring a one coordinate system in your CAD file, which will be at the center of your vehicle and at the rearmost position of your vehicle. After creating your FR coordinate system, you will be having few components for which the moment of inertia need to be applied. The specific component is needed to be selected and material properties are to be assigned. Once the material properties such as density and volume is assigned for the specific maneuver, you will be generating a preview report for each and every components. The preview report for CAD software such as Creo and SolidWorks are defined. In this preview report, the center of gravity, mass values, and moment of inertia in the inertia tensor values are obtained. These inertia values need to be applied at the specific cells. For position, you will be applying a center of mass values, that is, at the x position, you will be having the x coordinate system from R1 coordinate system to your specific component's geometry center of mass, y and z respectively. The mass of individual component will be applied, and then the moment of inertias are in the following manner. Xx value, xs, xx, axis value will be at the first column inertia, yy will be at the second, and zz will be at the third respectively. For each and every parameters, you will be applying the inertia values manually. Now, you might be wondering what the wheel carrier and wheel definitions are. For this, you can refer to the guidelines from user guide manual. From the user guide, in the vehicle modeling, at the vehicle dataset generator, in the assembly section, you will see different parameters for wheel carrier. Yeah. So in the chassis section at 9.3.6, you will be having a definition for wheel carrier as well as wheel. In the wheel carrier, you need to apply unsprung masses, but that should be non-rotating. For example, wheel carriers, brake calipers, rods, and other fixed elements which are under the section of unsprung mass. Whereas for the wheel, you will be applying the masses for individual components of wheels and brakes in which are rotating in the vehicle. Here, the FL represents the front and left wheel, whereas FR refers the front and right wheel of your vehicle. Similarly, RL is the rear left and RR is the rear right. Once you obtain the individual components moment of inertia, you can apply it in the software. Now, if there are multiple components in a specific section, such as for wheels, you need to enter the components of the hub as well as wheel. So you need to enter algebraic addition of individual components inertia and combined addition at the specific maneuver, specific position is to be entered. So hope you got the bit idea about how to apply moment of inertia, how to calculate it, and enter in the IPG section. Thank you.
Thank you, Rhythm. I hope it would have helped teams with understanding the coordinate system and the moment of inertia. So, teams, we will talk about more why moment of inertia is very crucial in optimizing your vehicle. So, with a certain degree of value change in moment of inertia itself, the vehicle behavior completely changes. So, we will go through why that is much needed and required to have a more accurate model that you are building. So now let's move on to the next session by Joe regarding IPG kinematics and MBS. So Joe, are you there?
I am.
Yeah. Okay. So you can start. Yeah.
So screen is good. Harish, can I get a confirmation?
Yeah. Your screen is as well.
Yeah. So hello guys. So I will be covering on how to model your kinematic behavior of your vehicle in IPG. So coming to kinematics, what essentially I mean by kinematics. So the basic definition of kinematics would be the motion of any body without considering the force that causes the motion. So in relevance to vehicle dynamics, so how the vehicle suspension system, how the tire and other part of the suspension system moves and interact with each other when this relative motion in the suspension system, when you're tackling on a bump or you're going on a corner. So there is a motion in the suspension system. So these systems will affect the parameters, your kinematic parameters. So we have to model this to actually run the vehicle. So let us consider, like, if you are running a simulation, your vehicle is moving. If you're taking a corner, your IPG has to know how your vehicle will be when it undergoes a compression. We have to tell the IPG like how your wheel is going to behave at each point of time. So that we have to model beforehand, and we have to input the parameters. So in IPG car maker, so if you can see from parameters, if you select car and go into suspension, so there is this tab called kinematics. So in kinematics, you can either create a linear BOF model of 2 or 3 degrees of freedom, or you can use an SKC, external file, or a MBS file, and to represent your vehicle's actual dynamics. So let me give you a difference between how the linear and non-linear works. SKC and MBS comes under non-linear kinematics, and this linear, as it says, is a linear. So in linear, what essentially you are doing is you are giving this static constant characteristic value, I would say. So from the guidelines, if you can see, so from the guidelines, as you can see, so these are the track, like this is a track change, wheelbase change, elevation caused by steering, camber angle, caster angle, toe angle, variations. These you are giving by a single characteristic value. This we have to calculate beforehand in your own kinematic software, whichever software you use, MATLAB or some other things, and you have already used your suspension geometry to calculate these values. That is the assumption. Then from that you have to take the characteristic constant. Let us say for compression of rotation, you give a value of 1.249 rad per meter. So that essentially means your toe variation is like for 1 meter of wheel travel, there is 1.249 radian change in the toe. So that is, if you translate to mm, like if you 20 compression, that is 1 degree of toe variation. So this is a constant value. For you have given a characteristic value, that means along the wheel travel, where as long as the degree of travel, like if it's 1 travel, it is constantly varying the particular parameter. But that is not actually true in an actual vehicle. As you see, in an actual vehicle, like if you consider the wheel travel of 100 for 0 to 20 let us take one parameter to understand this. Let us consider Ackermann percentage. So if from 0 to 20 of your wheel travel, the Ackermann percentage is around 50 to 60%. Maybe from 20 to 40 of your wheel travel, the Ackermann percentage can be 70 to 80%. It is not actually constant. But you cannot model this behavior in a linear DOF model. You need a non-linear DOF model in which you are mapping essentially every output of your kinematic behavior, like camber, caster, toe, KPI, Ackermann, to every point in the wheel travel and the steering travel. So that will give you an exact replica of how your vehicle behaves. This is a very simple characteristic representation. So why we are recommending you to use SKC or MBS file is because the motto of this year's IPG VDE presentation round and phase 2 and phase 3 are to allow you to use IPG software to optimize your own vehicle, to improve your own design. So if you are using a linear DOF model, you are not actually representing your actual vehicle. So when the simulation is running based on on a model which is not reflecting your actual design, you cannot optimize it effectively to bring about changes in your own actual design of the vehicle. So with this, I will now get into how to make a nonlinear kinematic model from SKC. As you can see, you can open the IPG kinematics from two ways. You can either go to file, and as you can see, there is IPG kinematics here. If you click on it, it will open. Another way is to from car suspension kinematics. If you are choosing SKC, and you can see. So if you are choosing SKC file, you can see the open kinematics button here. So when you press upon this, the IPG kinematics will open. So in IPG kinematics, this is the menu bar, and this is all the shortcut icons you get from where you can actually directly go to. But I would recommend you go from the menu bar step by step, so we'll understand the flow. So from file, we have to first select the type of suspension model we are building upon. So there are several models available in IPG car maker that you can choose based on your design. For this particular demo session, I will be using a double wishbone front suspension. I will be showcasing how to model a front double wishbone suspension system. So you can select from new the double wishbone I have selected. Now I go on to edit, and first I will set on the simulation controls. So simulation controls coming under that. So what all of these means essentially. So this kinematics forces on and off. What it does is calculate your inertial forces, the mass of the suspension components that you give and the vehicle. So it takes into account that when this is kinematics is the process is being done. So you can turn it either on or off. And the storage of tables is like when you actually run the kinematics here. So I will just run with this random data at the start. As you can see, it shows all the values like for the wheel travel 0 to 40 for the compression and 0 to -40 for the uh, elongation. So it shows all the value like toe, camber, track chain. These all values will be printed upon the screen if you press on log. If you just press on, or if you just keep it as on, you can choose the particular value that you want from this table parameter. So if you can choose on reciprocal compression, only those will be displayed. So if you base this is just a front end output that you want to select, and the storage on results. When you want to store your results, we need an SKC to input into CarMaker to run the vehicle. So we need to select either CarMaker interface 1 or CarMaker interface 2, whichever. There is nothing not much difference. The CarMaker interface 1 complaints is calculated linearly, and CarMaker interface 2 the complaints values are calculated non-linearly. But in actuality, we are not focusing on compliance as of now. We are just focusing on kinematics. So either one would do. And you check on this box, save car maker files only. And this square linker is just the name for the double wishbone system in kinematics. And comment you can add in whatever you want to recognize the same. And moving on, first, when after the general simulation controls we have selected we needed, then we move on to the kinematics. So in kinematics, as you can see, there are three tests that you can do. Parallel kinematics. So parallel kinematics in which is a simulation in which both of your wheels are moved up at the same time and moved down at the same time. So they are moved based on your compression. So these compression values, minimum and maximum, is the wheel travel and not the shock travel. So this wheel travel, so this is how much your wheel moves downwards from your designed position, and this is how much your wheel moves up from your designed position. This is a step size. So if you put step size as 1, for every 1 mm variation, all these values, wheel track, roll center height, toe, camber, everything will be calculated for each 1 mm. So this is just to give you for the interval between the printing of the actual outputs. So similarly, steering kinematics. So in steering kinematics, as you can see, there are off, on 1, on 2, and steering force. As you can see from this IPG kinematics manual, So this kinematics manual you can go through to understand each of the parameters in depth of detail if you ever forgot after this session. So if you turn on, the steering kinematics is calculated only on the static position. As to say, like your wheels are in the design position 0. Now the steering is moved to the left end and the right end, and the variation in all the kinematic parameters are calculated and displayed. So if you turn on 2, then the steering input along with wheel travel is calculated. So when you're going onto a bump and you're still steering, you need this data, because for the wheel travel of 10 mm, if a wheel is going on, then you are giving steering, then the actual value outputted would be different from just when you're steering in the static position. So you can use steering kinematics on or on 1 or on 2, and reciprocal kinematics. So reciprocal kinematics is the case in which the wheel travel is not same, like the left wheel is going up and the right wheel is going down, or vice versa. And there are 4 cases in which reciprocal kinematics can be done, which you can go through from this kinematics help manual. So we have set that the compression and the steering rack. Steering rack distance is essentially your rack travel. If you say you have an 80 mm of rack travel totally, then for the left you have 40, right you have 40 mm of rack travel. You just have to model that in here. And again, the step size is same as what before. For every 10 mm of rack travel, it will show you the outputs. And moving on to compliances. So compliances is like when the vehicle is actually moving, there are a lot of forces acting upon the vehicle, which causes some deformation and deflection in the suspension system. These deformation and deflection would actually cause some effects on your vehicle, like torque steer, brake steer, and we are not focusing upon that as of now. So we are just focusing on purely kinematic model. But if you have the data for this compliance data, like the forces acting upon your vehicle, you can proceed with this and also include this into your vehicle to get a more accurate representation of the actual vehicle. And for the compliance and mixed forces, just keep everything off if you don't have the data. And let's move on to the modeling of the vehicle data. First, now we have modeled set the simulation control. What we are going to simulate, that we have now modeled. Now we are going into the actual vehicle data. So in vehicle data, I would start from this general. From first, the tab is on general. So in general, if you see axle, front axle and rear axle, there are 2 options. So now double wishbone, if you're modeling on the front wheel, then we'll choose the front axle. And if you're modeling for the rear wheels, we'll choose the rear axle. And the brake force ratio is essentially the brake bias that you have in a vehicle. Like if you have a more forward heavy vehicle or a rear heavy, whatever in your case, and you have designed this brake system in which there are more brake forces sent to the front than the rear. And then you have to input the percentage, how much is the front more than the rear. That percentage ratio, you can see the exact you can read the manual for more understanding. And then you can select. Let me just keep it at 50-50 for as of now. And driving torque ratio. If you are, so we are all having a backup for all-wheel drive vehicles and four-wheel drive vehicles. In that such a case, how much is the torque ratio split between the front and rear? That ratio also you could input. And chassis subframe. So this is not likely in case of a BAJA vehicle. Like if you have a subframe that you're mounting onto your actual vehicle frame, and in the subframe you're connecting the suspension system. In such a case, you should turn this on. But mostly we do not have. So we can turn the subframe off. If you have subframe on your design, then you can actually turn this on. And next, the tire rate. So tire rate is your tire's property. So your tire property, actually, you have already created your own tire file. So from the tire file, you can actually get this data. So when you go to the car maker window, then go to parameters, then go to tire. In this tire, like if you go to the model parameters, you can see this vertical radial stiffness. So here it is in Newton per meter and it is in Newton per mm. So you just when I put this into here, it becomes 100 actually. So you have to make sure it is the same as your actual tire that you have bought. Whatever your tire you're using and tire data you are using in the tire data, you use the same here in the tire. And next, we move on to the vehicle center of gravity height. So vehicle center of gravity height, where would I get it? It is also already modeled because you are inputting all the masses of your vehicle and their locations in the car maker when you're parameterizing your vehicle. So the IPG car maker already knows the vehicle's COG height. So you go to your parameters, assembly, then you go to info. In info, you can see overall vehicle center of gravity and XYZ values. And the Z value is 0.598, essentially with 598 mm. So you just see that and input that here. And similarly, your design wheelbase, whatever you have inputted the parameters, same you can use. Let me just assume it is 1400 as of now. And the design positions. So coming to the design position, it is the static position when you are designing. You may design for a negative steer, zero wheel travel, or zero camber and such for your at zero wheel travel. So at zero wheel travel at design position, whatever you have designed to the vehicle to be, you can just input it. That just means just assume a zero for toe and zero for camber at zero wheel travel. Another thing is elastically mounting your steering gearbox. If you are mounting your steering gearbox to elastic wheels to the vehicle, then you can turn this off. This is just for the bushing properties. This doesn't. If you do not if you're not mounting it as such, just keep it as off. And let's move on to the spring. So spring fixing. So spring is essentially your shock absorber, and if you're using a separate damper and a spring, you can the spring is you can just focus on the spring and not on the damper. So in the spring fixing, you can fix where you are fixed. If you're fixing the spring to the lower wishbone, you can choose such. Or if you're fixing it to the upper wishbone, you can choose such. And stabilizer bar fixing. So if you have a stabilizer bar, then you can specify this. If not, you can just select none. And similar for pull and push rod. If you're not using such, those things, you can just select none. And for the spring, this is spring rate. As you can see, already you have modeled the spring rate in your parameters under suspension already. So you can just take that value and put it here. So for spring, now for this particular vehicle, it's like 20,000. So this is again in Newton meters and this is again in Newton mm. So you have to be careful about those units. So this is just 20 Newton per mm. One more thing is if you have a graphical data, so if you have a spring curve, it is always better to input a spring curve. So because like many teams are actually using the Fox float suspension, which do not have actually a straight line like constant spring rate. If you are actually using such a shock absorber, the advantage that you have is that your spring rate is not constant; it is varying. So if you want to actually translate that advantage that you have in your actual design vehicle to a simulation, you have to model it as such. Just by giving a constant spring rate, you are wasting your advantage that you have based on your shock absorber choices. And similarly for the stabilizer bar, if you have none, you put already none. So it doesn't matter what you give. You don't have to put zero because putting zero may cause an error in the end while running. Similarly for pull and pull shot, if you are putting none, just leave it as whatever value it is, just leave it as such. And stabilizer torsion bar, if you have, you can put the value. If you don't, you can select the none from here. And then moving on to bushings, we'll come to bushings later. We'll just first cover the mass. So here load, this load is there any additional load you want to put upon a suspension system. And other than that, these are all the component weights. You can go through the initial guidelines that we have released from BAJA for further details on how to input this mass. Essentially, just these are all the component weights. You have to use the component weights for here. And as Ritam already covered the wheel carrier and wheel, the rotating and non-rotating non-sprung masses that you can input here. And like chassis subframe, you do not have a chassis subframe, but you're still having a 50 kg mass. If you're not having this, just don't turn it to zero. Just keep it as one. Whatever things you are not using, but there is present here, you don't want them to be included. You just keep it as one, and do not put them as zero. That is very important because that may end up causing an error for you. And next, moving on to geometry. So this is geometry is actually when we are inputting all the coordinate points of our suspension system. Let me just show you how the coordinate points are here. For double wishbone, as you can see in this photo, from the IPG kinematics reference manual, page number 86. So this is the representation of all the points and the diagram. And all these points A, B, C, D, E, F, G, all the definitions are in here. So you can read this. And if you're not sure where each point is, you can always see this photo and find which point refers to which point. And you can take this from your scan software. I will just show you how to take a few points from the CAD software. So first, in the geometry, there are actually two standards: automobile industry and DIN 70,000. DIN 70,000 is the same coordinate system as you have used for FR1. So I would recommend that you use DIN 70,000 so also not cause confusion. But I would show you for both how to take values. So this is just a representation of a vehicle with the 3D sketch of the arms. So now in here, I have created two coordinate systems. So automobile standard and DIN 70,000. As you can see here, one second. In automobile standard, the x direction is facing towards the rear of the vehicle and is along the right side of the vehicle, and z is above towards the up. And this coordinate system is in the rearmost point. That is essentially FR1. You have to place this in FR1. And DIN 70,000, your x is for going through the you're going to the front of the vehicle, and your y-axis is pointing toward the left side of the vehicle, and the z is on the above. And this is also still in the FR1 point. So this is a difference between the two coordinate system that you have created. Now, for the kinematics. So here there are wheel center points, and this wheel carrier, lower wishbone, upper wishbone points. All points you can read the manual and see the photograph to understand what this points actually mean. Now let's say for this point is upper wishbone. So wheel carrier upper wishbone, I have this point. So I have to find this point distance from my coordinate system DIN 70,000. I have to. So now I have selected this, and I have selected the relative system is DIN 70,000. Now I have an x, y, z value, x 1549.19, y. So I can directly input this to my wheel carrier upper wishbone. I just select this x value 1549, y value minus 548.99, and z value 361.82. Now I have imported this value from my CAD software. As such, you have to do for every point. Now, similarly, when you are putting a value in geometry, you also have to put it in bushings. Not for every point, but for most points, there is a like what do you say? Wherever the points you are using bushings, so that points there you also have to put in here. So there is let's just take the front and rear pivot points of upper wishbone now. So consider this as now I'm just inputting this. So this is my front upper wishbone rear pivot point. So this rear pivot point now I have the data. So I am like inputting that here. So upper wishbone rear pivot point. Now I'm just inputting 150405, and this value is minus 21186, and this value is 438.28. I have inputted here body bushing rear upper wishbone. So now here there is also the same point here. So this point bushing bushing center. This point is essentially the same point that I have input in the geometry. So I can put the same values here for the x, y, and z. 1505, and this I'll put minus 211.86, and this again 438.28. I inputted. Now there is one more point on the bushing axis. So what does this mean? So if you as you can see, this line is the bushing axis. So this is a line of the bushing axis. Essentially, this like if you consider these as mounts, the bolt that will be connecting the arm would come along this axis. So this is your bushing axis. So this is the center point of your bushing, and bushing axis is just any point along this line. Just keep a point there. Just keep a point there and calculate the value for that particular point. Now I again go to evaluate measure. Now I select this point instead of the center point. Now it gives another value to me, and this value I have to input for the point on bushing axis. It's almost the same, like a slight differences. So this will essentially give the kinematics an idea of how your bushing is actually. Which is straight to the ground plane or not. Those kind of information. Now I'm again inputting the same. See, as you see, this is how you input a point bushing center and a point on bushing axis. So similarly, you have to put for all the values here in geometry, uh, most likely based on DIN 70,000. And for when you are inputting any values, if you are not sure about some values, like these values, you are not using these points anyways. You have already turned this off, like you have given none already. In that case, you don't have to again model all these values. You don't have to put zero. Just leave it as B. It will not be calculated when you calculate kinematic behavior. For whatever values you are not, that is not in your design, just leave it be. So you have to give for all the points, like for a normal vehicle, you have to cover up all the points. Uh, then you also have to go to the bushing and here, like subframe is not your, since you don't have subframe, you can leave it as such. Lower wishbone front and rear, upper wishbone front and rear, and your steering rod to the steering rack and the wheel suspension. These 6 points you have to give the point on bushing center, the center of your connecting point. And when you're connecting a bolt and if this is moving about a particular axis, the center of the bolt, this will move up and down or sideways. So that particular center axis, from that axis, you have to displace from the center point and take that value again. And again, you have to input on point on bushing axis. So this is how you model your geometry here. So when you are done with the entire model, when you have inputted all the necessary data from your CAD to this, then you can run your simulation. So if you click on run, let me keep, I will show you the, when I keep the log on, it is showing every value. Every value is being continuously printed on this log table. As you have to wait for some time before this finishes. When you are keeping a step sizes too low, it may take a lot of time. So you have to be patient with this. If your system is not struggling, you can keep a step size a bit higher for a initial higher result. So here you can see all the values, how the wheel travel, along the wheel travel, what is the variations happening, and the reciprocal kinematics, what are the wheel travel for the left and right wheel travel. Here the left and right wheel travels are different. So in that case, how your roll center height, roll center properties, camber properties, toe properties, those are varying. You can all picture from here. So now I will show you like a complete model. Since I don't have time, I'll just move on to the complete model. So this model. So here, let me give you another idea, like how to change these values to optimize your vehicle. So now you see, like anti-dive property. So now anti-dive property is at minus 22%. So now I want to have some anti-dive properties. So in wheel carrier upper wishbone, so I will show you how to model this. In wheel carrier upper wishbone, you can see the Z value. No, actually the 1 second. Your bushing upper wishbone. Yeah. So in your bushing upper front wishbone, the Z value is 619.77 right now. Now I am changing it to 680 and I am again running it. So initially the anti-dive property, you don't have any anti-dive property at all. But now I'm running it again. So now it's running on the back end, calculating each of the parameters right now. And now you can see. So anti-dive now is actually at 50% anti-dive. Now you have created for your vehicle. Because now your wishbone is more angled, the lower and upper wishbone will meet earlier. and now that will cause your anti-dive properties to improve. So this is one way when you can change the points to change these values. But what this also created is that my toe is increased exponentially, because you have to each time when you make such a change here, you have to go to the actual CAD model and see if it is affecting any other point. So from this, by changing these all values, you can find an optimized result. Probably most of your teams are already doing this in your own kinematic software. If you can also consider this as an option to make the improvement. If some teams are not using, you can use this directly for your kinematic behavior test. So now I will stop this and I will show you another change. So now you can vehicle data. I will change this back to 619. And now you take the wheel thyroid points. So wheel carrier steering rod. So your tie rod is connected to the wheel carrier at the Z height of 430. Now I'm changing it to 500. So when I change the points there, I also have to change the point in bushing center. So if I don't change the point in bushing center, it will show a mismatch of values that are happening. So you have to make sure you change in both the geometry and the bushing properties. Now you can say the toe is very high, like it's going up to 1,000 units. So we just when you try to change the height of the vehicle, what happens is in the background, the IC points of your upper wishbone, lower wishbone, and steering rod all have to meet at the same point. If they are not meeting at the same point, there will be some toe change when they are moving along the wheel travel. Now I again go to the vehicle data. I go to geometry. Now in the steering rod, I'm changing it to 415. Now I again run this. So now initially it went to 1,000 minutes. Now it's only going up to 445 minutes. Now you can see the variation there, and initially it's only 60 minutes. So similarly, based on your design, you can input those values here and see the actual change of the camber, caster, or whatever it is. So here you see caster initially is like 19.26 degree. Is it actually your design caster? If it's not your design caster, then you have to make sure to change the points such as it reflects correctly. So after the view design is done and you're inputting this, from these tabular values, you can change your points in the actual design. You can create a iteration loop between your SolidWorks or whatever CAD software you're using, that design and this, to find that optimized balance between all the points. So that is how you input the kinematics file and use it for optimization of your suspension behavior. Hope you all have understood this. Now, just for saving your SKC file and inputting it as same. As I said earlier, in the edit simulation control, the save a CarMaker file should be turned on and storage of results should be in CarMaker interface 1, CarMaker interface 2. Now you click on file. Now you click on save. And now you choose any particular name. I'll just say trial double wishbone. And you save the input data kin file. You just have to save the kin file and it will save the SKC file automatically. There is no particular separate SKC file in the filter document. Just after turning it on, you just click on whatever name you want and save the kin file. Now when you go to the data, you will see trial double wishbone front SKC file present there. We have saved only the kin file and SKC file will be saved along with it when you make that such. Now let me show you. Like in parameters, you just go there. Kinematics, we go there already. So for the rear, I'll just keep it as linear 1D. And for the front, now we have model and SKC file. Now we are selecting the model. You open the model, you go to the folder where you have saved. Now you can see trial double wishbone SKC, the one that I saved just now. You select on that. Now your SKC is doing both your kinematics and compliance for you. And now I'll just run a sample test track of straight line running. I'll just showcase. It's still working. So when you're running, you may get a lot of errors if you're not following the process properly. You just have to check after you modeled it. You just start running it and make sure that it's not showcase any error. As you can see now, it's running perfectly with the SKC file. So that is how you create an SKC file uh, to model your non-linear dynamics, non-linear kinematics, actually. So now that is one way of doing this. So another way of doing this is use a MBS file. So MBS, how do you open an MBS file? So go to suspension and just select MBS here. And from this MBS, you select open MBS editor. This MBS editor will open up. So in this MBS editor, actually, you have very limited number of suspension model. You have just 4. So it is very limited. So if you you can, I will most likely recommend to do an SKC file over an MBS file. So you can use a double wishbone axle and dynamic. So regarding all the MBS file and how to make it, you can get that from the IPG user guide. IPG user guide you can open from just help. And if you go to user guide, you can open up the IPG user guide. All data about MBS non-linear kinematics model is there. In there, MBS is actually present here. For the IPG kinematics, you can actually have to open help from the IPG kinematics itself to see the reference manual. So only here, let me initially the dynamic, you can for the symmetrical suspension. If you put symmetrical suspension, then you just have to put for either left or right design. You just have to make sure one is doing one left or right. You can input the data you have. You will replicate the same for the right side. Now you have to make sure for having steering system or not. Extended configuration in this in the case you want to include a steering box and a subframe. Steering gearbox and a subframe. You have to, if you want to include, you can turn extended configuration on. Calculation mode either in dynamic or accelerated 2D table. Dynamic actually gives you more accurate results based on all of the complaints data and every data together rather than accelerator. And initially now we have set it. Now in this MBS, we have set the suspension model. We have told it that it is a symmetrical suspension. We have told it we are modeling with the series subsystem. Now essentially we are modeling again front double wishbone suspension system. Now here it comes the body. So in this bodies, you can for the wheel carrier, lower left, upper right, and you all this data you have in your parameter already. So as you can see in the wheel carrier chassis, you have all the masses of the points. And another point to note here is MBS actually calculates everything from the F1 suspension point, F1 suspension coordinate system. I will cover that when moving to joints. So here just you have to put the input of all your wheel carrier, rubber stone, spring, damper. If it's the same, just make it as half and put input here. And you calculate your for the moment of inertia, as Sritam explained previously, calculate the moment of inertia from there and input those values here. If you do not have those values, so don't worry about it. Just leave it as what already it has been, stabilizer bar and stabilizer link. And when moving on to the joints, first you have to tell MBS the origin of FR frame, vehicle frame FRB with respect to FR suspension vehicle data frame. So what is FR suspension? Where is it essentially? So I will showcase you that. So I have created a FR suspension. See, this is essentially FR suspension coordinate system center point. So the center of your wheel, left and right wheel center axis. If you connect the left and right wheel centers on the front, the center point in the middle of your vehicle. So that is FR suspension. And the direction is essentially same as FRD. X is pointing toward the front of the vehicle and Y pointing to the left of the vehicle and Z is pointing above. So first, initially, what you have to input is the distance of FRD within 70,000 from your FRD. So I will just measure within 70,000 from FR suspension. Now I have some XYZ values. So these XYZ values, I have to input to the origin of the vehicle frame FRD. I will input those values here. And similarly for the wheel carrier wishbone lower left, and your wheel carrier wishbone upper left, and the steering rod. This left is essentially means it is the left side of the vehicle. So only you're modeling for the left wheel, the right is grayed out because we have given it as symmetrical suspension. And similarly for wheel carrier left and steering rod left and the vehicle stabilizer bar. If you don't have it, just leave it be. Just from similarly how we did for how I showcase for SKC, select everything with respect to FR suspension points. So FR suspension origin, not the FRD origin, FR suspension origin, to input all of these points. Then moving on to the force element, this essentially is just the spring and your damper. If this is the same for you, just input the same point for both of them. And where are you mounting your spring, upper and lower wishbone? Unfortunately, there is no option for upper wishbone here. So if you are having an upper wishbone, most likely you can use the SKC rather than this. So there are only two options, lower wishbone and the wheel carrier. You can choose for all three. And then we move on to bushings. So in bushings are similar to what I showcased earlier. Choose the bushing for all these four values. The bushing center is also I told earlier to take the bushing center point, essentially where the center of your bush and the bolt along the point which is the kinematic is happening, that you input as position. And position on x-axis similar to what we did on SKC, just on the x-axis along the line of the axis, just take any other point and input the value same here. And there is another point here in addition, different from XKC, that point on XY plane. So XY plane, as you can see, you should take that line and for that line, you are making it as a plane by drawing it in 3D behind. So now you have a plane behind that line. So in this plane, you can take any random point here. So this, so as you can give you a real good idea. So this is the Y direction, I would say, the Y direction of the vehicle, Y axis of the vehicle. There is a distance we are adding in the Y direction and getting back of that point. So let me showcase it in a SolidWorks section. So now this is the line you have as your bushing axis. So now you have to draw a plane. So now this entire area is in the plane of the bushing axis. So now in this plane, just choose any point. Choose any one point and input those values here. So this will give you the like this is like the plane. If you rotate it 360 degree, you will get the entire bush. So just input all those points for here. Then your bushing is done. Then for the mapping, this is similar to the things we did in SKC, like the step values. So maximum compression you have to define. Here it is in meters. So just if it's 0.1, this is 100 meters of compression and steering rack travel, the maximum travel that you have. You just input those values here, and the number of grid points is essentially your step size. If it's 17, the 100 would be divided by 17, and for each value, you would get an actual output. And similarly, for miscellaneous, you can keep the static camber and toe angles. You can keep it as such. After you model all of these, you can go through this user guide from page number 385. Keep it along with you when you're using this MBS file. Then you can save it. You can just save it. I just put it as wishbone. I will save it as MBS. So it is now saved in the same location. So I again go to car. I will go to suspension. I'll go to kinematics, and now I have chosen the MBS file. Now I have to select the model. I'll just press open. And as you can see, dial rubber wishbone MBS.mbs file is created. Now I select this model. Now this model is being applied. So this is how you model in an MBS, similarly how you did to SKC. But you cannot get those optimization values or data directly from MBS. You have to get it from IPG control after running the vehicle, which is a bit of a tedious process. So for optimizing SKC, it gives a lot more speed in MBS, I would say. That is how you model a non-linear kinematics of your vehicle to IPG. So with this, I'm ending this session. So thank you.
Yeah, thank you, Joe. So teams, I hope you had understood how to model an SKC in detail. Thank you so much, Joe. It was a very informative session. Teams, for the virtual dynamic presentation round and the VDE simulation round, it is recommended that you use an SKC or an MBS file. But you can also go for an DOF model. But it is recommended to use an SKC file because you will have a more precise vehicle behavior in your simulations, and you will have you will see the difference in the results that you get for a normal linear DOF model and an SKC file. So a DOF model basically, let's say a 1 degree DOF model basically works on vertical axis only. So it will not model other behavior or in other behavior in other axis. So yeah. So and the second thing is that we will be starting the next session after a short break of 15 minutes. So we will start around, let's say, 11 o'clock. And we will go through each vehicle dynamic scenarios that you will be simulating at your own end, and will be presenting the results to the static in the static event to the judges. So we will go through what all is expected, or what kind of results or what kind of output plots is expected in general. So you can also explore or add more results in your presentations as well. But it is basic things which are expected for each virtual dynamic scenarios, and the short theory about each dynamic scenarios and basic understanding about it, and what kind of results that you are normally getting for your vehicle, which is actually not ideal or realistic for a real vehicle to behave as, is also what we will be covering in the second part of this session. So we will go for a short 15 minutes break. So you can stay on the call, and yeah, we will start at 11 o'clock. So, hi teams, we are back. So, we will now start with the second session. So, you can call your teammates who had left meanwhile and tell them to join. So, uh, by the time they join, I would just like to mention one thing that I forgot. So, in the SKC session that Joe had conducted, so one of the main questions that we get from you is that how to model a charm system for the rear. Now, in SKC or in MBS, you don't have a specific model present to model an charm system. So that can be done. For that, you could use either a 1-degree DOF model for the rear, which can perfectly model your vertical wheel movement for the rear. So you'll not have any steering, right? So you can use the 1-degree DOF model, or you can use MBS and explore on building an HRM or some other system if you have, let's say, trailing arm, semi-trailing arm for the rear. So, but for the front, it is recommended that you use a SKC file to model your front geometry precise and the behavior as well. So now, I hope you have informed your members. So we'll start with the first session, first dynamic scenario of the second part of the session, which is the acceleration test. So is my screen visible? Can anyone just confirm?
Visible.
Okay, thanks. So before I start with the acceleration test and what all the load scenario is or the load case or the end condition or the boundary conditions, basically, sorry, the boundary conditions for this scenario and how you have to set up your scenario, the maneuver commands, and what all the outputs are basic outputs that are expected, and you can, and the factors that are involving in optimizing your acceleration performance. So I'll be covering, I'll be keeping it very brief because acceleration test and the brake test is something that all teams are aware of. And also you can search for the ISO standard. So ISO is basically the International Organization for Standardization. So particularly for vehicle dynamics, we have different ISO standards. So for acceleration and brake as well, we have, and for different scenarios in the variation in scenarios in brake test itself, we have different ISO standards. So for that understanding, you can explore on your own and do some research as well. But for the other test cases or other load cases, such as your on-center step steer and CRC, which is constant radius and cornering, constant radius cornering test, which we will be covering in this session. For those, we will be diving a deep into the theoretical aspects as well, and also mention the various ISO standards which comes into play for those scenarios. Now, before I begin with my presentation for acceleration test, so I have already loaded a product example. So again, the braking example that I had shown before. So this is just to give you a bit of understanding. So let's say you have this vehicle data set, right? So you have built your BAJA vehicle, you have mentioned all your moment of inertia values as it was mentioned by Rhythm in the coordinate system and moment of inertia session. And also you have, let's say you have used an SKC file as Joe had mentioned earlier, how to build an SKC file. So after doing all of that, so now if you go and press on this info file, so I had mentioned before that I'll be talking a bit about this. So this is the basic information that you get for your vehicle, which is the overall mass, the center of gravity position, and the inertia tensor value. So let's say mass and the gravity position is something that you understand. So this gravity position X, Y, Z, this is basically the X, Y, and Z. And with respect to the FR1. So if you go to the graphics, you will have the FR1, and with respect to that, you have your mass location. So visually also you can understand where is your, this will be your wheelbase, this is your track width for the rear and the front, and somewhere here you will have your, let's say, center of gravity or center of mass. So when coming to the inertia tensor, so this is basically a 3x3 matrix. So this values that you are seeing here is basically a 3x3 matrix, which basically represents how your mass is distributed relative to your center of mass, and represents, and these values, right? The diagonal values are your X, Y, and Z, which is basically your overall moment of inertia of the vehicle. So it's actually useful, very useful to understanding the how the vehicle responds to torque and rotational forces, which are basically affecting the handling characteristics of the vehicle. So let's say X is your roll axis, right? So if the value is high, then your vehicle would feel more stable in your corners, and because your roll response will be slow because the value is higher for the X. But if that value goes too high, your vehicle would feel very sluggish. Or let's say if you are having a very abrupt or sudden maneuver or sudden turning that you're doing, which you will be doing in on center and steer step scenarios, we will be looking into that. So in that test scenarios, you have to give sudden maneuvers. So in that, if these values are too high for, let's say, for the X, your vehicle would be very sluggish, and it will not rapidly change direction. So it has to be between that sweet spot that you have to find. So for each vehicle, the value changes. There's nothing like a definite value or range that has to be followed. So for your vehicle, mass, center of gravity, the wheelbase track width, and other, let's say, gyration radius and other axle loads for front and the rear, based on that your this value would be changing. So this is just for representation. This will give you an idea like how much you can simulate, and you can compare at your end, and you can understand like how much your vehicle behavior is changing with the range of values that you are having here to see. So and this whole window basically shows the physical characteristic values or the physical parameters which defines the basic performance of the vehicle. So now moving on to the acceleration scenario. So acceleration test is something that we also have for the phase 3 event as well, right? So it is a we have the event for, let's say, 150 feet. It is 150 feet. So you will accelerate, and we basically measure how much time it takes for your vehicle to reach the end, basically. So, but in this software in IPG CarMaker, we can go one step beyond, and we can understand more how different parameters, vehicle dynamic characteristic values, or vehicle characteristic values are coming up, and how the vehicle is actually behaving. So if our model is more precise, so of course you will have a more realistic outputs in your simulation. So the whole objective of the vehicle acceleration test is to do a performance benchmarking, basically, or how your engine data is, if you are achieving that high RPM at that CVT ratio or not, if you are achieving the high torque of, let's say, 80 Newton meter for MBAHA vehicles or not, or if you are EBAHA, your motor power consumption is within that 9 kilowatt or not, and also the pitch behavior, basically. If it is a too much, if, let's say, in the acceleration event, if there is a too much squat, then the behavior will be, let's say the squat angle is almost more than 10 degrees or 12 degrees or 15 degrees. It will be very it is not a good performance value. The values are too high, so the vehicle will not be performing well. It's not stable, and comforting as well. So, but in Baja vehicle generally, ride comfort doesn't come into picture because you are running in an off-road condition, right? So you will be driving in an off-road condition. So ride characteristics are not that important, but handling is very important. So pitch can affect that as well. So and the traction system or the acceleration values or the torque values that you have inputted for your model, how much are you achieving that expected range or the expected value that you had done through your hand calculations in actual reality itself that you can find out. So the basic factors that are affecting the dynamics is the powertrain characteristics, of course, the engine data, the motor data that you input, and also the driveline torques and the moment of inertia as well for both the driveline and for other areas as well, and the overall load distribution. So all this you can also get a basic understanding from the info option that I had shown before, and also your anti-dive and anti-spot values, how much you have. So if you are using an SKC file, you can influence this value can also come into picture, and you can make it more realistic, give a realistic behavior to the vehicle. So moving forward with the scenario and the maneuver command. So for the acceleration test, it is very simple. So before I get into the scenario, so let me just show you the scenario editor. So as you are aware, you have the software. So you could have seen that in general, the whole the GUI has changed a bit. So from here itself at the top left, you can just switch between your maneuver command and your scenario editor as well. So this is a product example. Basically, this is not the actual track for the acceleration event, but let's say if you want to build your own tracks, right? So you can just click on this road. You can right click here. You can just press a straight, and then you can create your own road. So and let's say if you want to give the length of the road, so you can change it to, let's say, 150 feet is almost 47.5 meters, right? So it is asking the value in meters. So you just enter that, and your road will get created. Now, if you want to give the path, the driving path, right? So the route. So this is something that you are already aware of. I'm just mentioning that for your understanding. So you just give start new route, and if you have, so right now the yellow color box would not be visible because okay, so vehicle is loaded. Yeah, so okay, just go ahead. Okay, so the route is created. So your vehicle is ready to run for this. And there are other options as well. So if you are into, as I mentioned before, that you can also include various other scenarios as well, other than the 5 virtual dynamic scenarios. So you can build your own scenarios using the different options. You have road, turn, point list, etc. You can also, let's say, you can create a gradability event or a gradability scenario kind of a thing, or you can do something different, from your own imaginations, or yeah, and you can include that in your presentations as well. Now, coming to the maneuver window. So in the maneuver window, the main change is like the whole GUI here is as well has changed. So already in before versions it was known as global settings, so now it has changed to maneuver settings. So don't get confused because of that. And in this, let's say you have the maneuver 0, and in that you will be defining your maneuvers driver models for longitudinal and lateral dynamics. So for both for longitudinal you have IPG driver, speed control, menu pedals, and stop vehicle, and etc., which I'm sure you are already aware. And of course for lateral dynamics also you have your sign, steps, steer step, follow course, and lane change. So we will be you will get a bit understanding more about the sign and the steer step and where it has to be used in the following sessions. And also if you are using your own mini maneuver commands, you can just right click on this and you can just mention, let's say, car.ay, and we will be mentioning as well some mini maneuver commands that you have to mention here in the following sessions for particular load cases that you have to strictly follow, because that would be calculating and giving you some values which will be used further in the simulation. So, and apart from that, yeah, so apart from that, this is the basic introduction to the GUI interface that I wanted to give. So let's now look into the acceleration test run that I have already created. So yeah, so now moving to the scenario. So you will have a straight road. You would have to create a straight road. So for acceleration on brakes, you have to create your own scenarios. For the other three scenarios, you can or the load cases, you can use it, the road file, you can use it from the product examples. So the team will be mentioning about those as well in their following sessions. Now, it's a basic track for the acceleration event. You just need to create a straight road. So the length of the road has to be, yeah. So the length of the road has to be 45.7, which is 150 feet. And then the another main crucial parameter that you have to ensure is you can just press on this green button here. And once you press that, you will have this reference line and all that will be shown. Again, press it, and then you will get the parameters that you can define here. So you need to make sure that the friction value is 0.7, right? So in guidelines as well, normally the road friction value is taken as 0.7, it is mentioned. So you need to make sure that it is 0.7. So if you are using any other product example road tracks, so normally the friction value would be something else. It could be 1, it could be 0.5, or it could be 0.8. So you need to make sure that you change it to 0.7, and you need to strictly follow that. And then for the maneuver commands for the acceleration event, now coming to the maneuver window. So let's say you only have a single maneuver. So the end condition will be that your car velocity should be greater than or equal to 16.667, so which is 60 kilometers per hour in kmph. And then you will use a longitudinal dynamics as manual pedal. Your throttle will be 1 and your gear will be 1. So if you are using a CVT for MBAHA most cases and NH-BAHA, you will be inputting the gear as 1. If you are using an EBAHA and you are not using any CVT, so you can just leave this as blank. In the maneuver setting window, yeah, sorry. So this is not required. So in the maneuver setting window, you can put the gear value as 0. And other start velocity and the lane change and other values as 0 as well. So once you're done with this, defining this simple maneuver, you can just start with simulation. So let me just start. So I hope you are following me at your end as well. You are doing the simulations at your end as well. So just a minute. Okay, so as you can see, for this vehicle, even though the whole track is 150 feet, right? But the vehicle has reached the 60 speed at, let's say, 3 seconds, right? So even before completing the track, the vehicle has reached the 60, and because the end condition was 60 kilometer per hour, the vehicle has stopped. So this could also happen to you, but you should not just go with this and just see, like, just say that you are achieving a very, good acceleration for a very short distance, or vehicle is very, improved. But so to give you a gist of it, so let's say you have this GG diagram here as well. So you can see the values which are, going from minus 11 to 11, like almost like too high, right? So or sorry, the longitudinal is 45 to minus 45, so which is really unrealistic. So what I mean by that is, let me just open IPG control now. So in IPG control, I'll just plot car.p, and I'll also plot car.ax, okay, which is the instantaneous longitudinal acceleration, right? So yeah, so if I just simulate this again, yeah, okay. So you can see that even though your velocity is increasing, that's fine, but your instantaneous acceleration is too high. It is almost 50 to minus 50, okay, meter per second square, which is unrealistic, okay, which is not an ideal behavior of a vehicle. Okay, so if I give you a max value also, it is around 50. So it's something that you need to check. I'm sure you will also be having the same kind of results for your vehicle. So to improve this, what you could do is you could just follow the factors that I mentioned, right? So moment of inertia, load distribution, and your powertrain moment of inertia ratios, and other, let's say your torque and transmission ratio. So that also affects it. So if you fine tune it more, you will get a very realistic value. So let's say this is the output that I was getting. So I have only taken an output for two parameters, which is longitudinal acceleration and the pitch value. So you can also include more parameters, let's say your engine RPM, or engine power or engine torque for in BAJA vehicles, for example. So, and in this graph, as you could see, so as I mentioned before as well, the maximum value is around 50, but it has to be less than 1G. Okay, so this you need to make sure, because for an ideal BAJA vehicle or for road car vehicle itself, the ideal acceleration value has to be less than around 1G or less than 1G for it to be safe, or have a very realistic performance. And also the pitch value, you could see that it is going more than 7 degrees, negative 7 degrees, right? So so if the pitch value is negative, then it is basically squat that is happening, and if the pitch value is positive, then it is basically the type. So in braking test, we will look into that, but more towards for the acceleration test, as the values are too high, like it's around more than minus 7 degrees. So it has to be less than 7 degrees for it to be in a very stable condition. You need to make sure that it's around that value, at least less than 7 that you are achieving. And also uh, 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 other parameters are also there, like that you need to make sure are under safe limits. So you can do some research at your own end and see what are could be the range for those parameters, and yeah, include in your presentations. So now let's say to give you an idea of the improved version, let's say, so here again the acceleration value that I plotted. So the maximum is going around 6 meter per second square, which is less than 1G, right? So this is ideal behavior. And then the reason why this at this instant, or the starting instant between 0 to 1, the value is higher is because your vehicle is actually accelerating. Your power is going down from your engine to your wheels. So the vehicle is accelerating, and as it's accelerating, and the vehicle is the acceleration value is over a period of time is trying to get constant or parabolically decrease to a certain value, the velocity is also increasing and reaching the maximum velocity. And then for the pitch as well, at the beginning of when your acceleration is high, your pitch is around -1, right? So it's less squat, it's more stable, and then it's becoming 0 as the vehicle gets stable over a period of time. So yeah, so that is all for the acceleration test. So you can also include some other graphs or parameters in your simulations, and show that during your presentation. And yeah, that's it from my side. Yeah, thank you. So now we will Rhythm will take over to talk about the brake test. So Rhythm, are you there?
Yes. So coming to the brake test, at very first, similar to the acceleration, we will go with the brakes. The main objective for brake is to perform the stopping distance as well as the optimized pitch angle for our vehicle. Similarly, weight transfer during the brake test conditions can also be optimized. Same, same as for the scenario, uh, similar to the acceleration, we will also create some roads for the brake, input some acceleration, constant speed, and brake commands, and then we will check for the outputs. Coming to the brake scenario, we will we will be having a scenario editor in which we will creating a 100-meter long track from the reference line, and in the segment we will go and check for the 100-meter long track. Ensure we will also make the friction coefficient to be 0.7. Thus, after creating a simple straight road of 100-meter long track and 0.7 as a friction coefficient, we, the road scenario is completed. Now, coming for the maneuver part, we will also we will apply three maneuver commands. At very first, we will accelerate our vehicle to reach the velocity of 40 kmph, and then let the vehicle be stabilized for 3 seconds. And after getting a stable vehicle, we will be applying a 100% brake. At very first, to accelerate the vehicle till 40 kmph, we will apply the end condition of car.v is greater than or equals to 11.11, that is 40 kmph in meter per second. Similarly, for the stable condition, we will apply a duration of 3 seconds in the time constraint dialog box. Then we will make the vehicle stop until the velocity reaches to 0.001. Thus, the vehicle will stop. For each and every command, we will have the longitudinal dynamics inputs. That is, for acceleration, we will apply the longitudinal dynamics as manual pedal, throttle and gear will be at 1. For throttle, the 1 value represents 100% and the gear 1 is the position of the gear. Similarly, for the stable condition, we will use a speed control maneuver from our vehicle options. The speed will be of 40 kmph and maximum deviation is set as 0 and sensitivity as 1. Ensure you uncheck the manual gear shifting at this condition. Now, the brake command is used to optimize the stopping distance of the vehicle. For this, we first evaluate the stopping distance. To evaluate stopping distance, we will apply the condition that until the car.v, which is car velocity, reaches to 0, we will log a parameter called dm.long.step distance. Oh, this is the UAQ used to calculate the step distance covered by the driver to its vehicle in the longitudinal axis. Now, after creating these maneuver commands, we can successfully run our vehicle by selecting our car. To ensure we have selected the optimum car, we will go in the parameters and check for each and every parameters. Now we can check for the brake parameters that are brake pedal, brake force, A2 master cylinder pressure ratio, response time, build-up time, etc. For each of these parameters, you can refer to the user guide, which is present at the UI, GUI in the help section. By accessing the GUI at the vehicle, If the vehicle model parameters in the brake section, you will be having all these definitions. That is in the section 9.15. For each and every parameters, you can refer this guide, this user guide for your reference and parameterize your vehicle. After creating a successful vehicle, we will run our vehicle and obtain some of the outputs. Let's start our simulation. Once the simulation has run completely, you can go to the control section and check for some outputs. Similar to the acceleration, you need to select outputs such as car acceleration. On running the parameter are being recorded. You can make the graph totally fit for easy understanding. Here, you can check for each and every vehicle's output. For example, the acceleration is first increasing as our maneuver command states, and then it will decrease until the velocity reaches to 40. After few seconds, it will stabilize for 3 seconds and then a sudden brake will apply. This braking condition will decelerate our vehicle and hence the sudden drop in acceleration value is observed. Similarly, the velocity first increases then decreases at the end. On the other hand, for the pitch, when the acceleration takes place, it goes to the negative value, and then for the braking condition, as the vehicle turns into the dive condition, it reaches to the maximum value. You can check for each and every values by clicking on the graph and then use your shift plus cursor to obtain all these values. You can check for the maximum speed as 44, pitch to be 9.27. This pitch value is too much high for our vehicles, which is a very unrealistic condition. So let's check for each and every graphs. At very first, the pre-optimized results which we have obtained is deceleration of 8.71, pitch angle is 9.27, and the stopping distance is 9.5, which are way unrealistic than the actual conditions. Now, after figuring out this issue, we can redefine our calculations and apply the new values to each and every conditions which we think might be affecting. If you think you can change, if you are changing your positions in mass placements, such as now if you are having some optimized design and changing your mass distribution, then you can also apply those conditions before performing a new brake test. Confirming optimized results for each and every vehicle, you can rerun your test with another vehicle file. For example, I choose another file. Here I have inputted some different brake parameters and different conditions which will allow me to optimize my vehicle. I will rerun the simulation and then I will obtain different parameters. After optimizing, I can recalculate my values such as deceleration is also decreased, whereas pitch and stopping distance is very much realistic. These conditions, yeah, these conditions can be verified with the graphs, and hence the stopping distance and the optimized value can be obtained. To check for the stopping distance, you can also go in the UAQ where we have created the uh, user accessible quantity, that is dm.long.step. This command is used to log the stopping distance which can be obtained from the UAQ, which is with which you can access from the direct variable access section. For this, you can go in the application and click on direct variable access. You can check for different UAQs also. Here, the stopping distance can be optimized. Similarly, you can obtain any of the parameters you want and redefine your brake maneuver to optimize it. Hope you, hope you can now obtain you got the idea about how you can optimize parameters and redefine them. Thank you.
Thank you, Rhythm. So, teams, I hope you have been following along with us. It's okay if not also as well. If it's okay. So, yeah. So another thing that I wanted to mention is that it is strictly teams are strictly have to follow the scenario and the maneuvers that we are talking about here in our presentations for each load case. So the same scenarios and the maneuvers will be mentioned in the guidelines that we will be releasing for the VDE presentation round. And you have to strictly follow those to generate the graphs or the results that you're getting for your vehicle model for the particular simulation. So now let's get started with the next load case. So we will be starting with the constant radius cornering. So we have Kamal with us, and yeah, he will be taking us through the constant radius cornering test, and which is very new, and I'm sure most of you would not have heard about it. So we will also be touching about theory aspects as well, as I mentioned before. So Kamal, are you there? We can start if you're ready.
Yes, am I audible?
Yeah, you're audible. Yeah, loud and clear.
Okay. Let me share the screen. Is my screen visible? Is my screen visible, Hari?
Yes, Kamal, it is visible.
Okay. Very good morning, teams. Hope you all had a great session on acceleration and braking after the break. So now we will just move on to the next session. It's a very interesting session on optimization of shock stiffness for vehicle handling. So before going on to the presentations, I want to just give a agenda of this session so the teams can know what they can expect from this session and what they can match it with the learnings which they have made. So the agenda of this session is to introduce the teams to vehicle handling, just a small introduction. Then we'll move on to parameters used to validate vehicle handling. Then we will understand understeer gradient is one of the parameters, and we will understand in detail about understeer gradient. Then we'll move on to the expressions or mathematical ways in which understeer gradient is being expressed. Then we'll move on to the load case, which is being used used in many cases in many industries, in many automotive industries, to get the understeer gradient of the vehicle. So then we'll move on to the IPG user interface, where we'll be loading a BAJA vehicle model, and we'll be doing the constant radius cornering test case. Then, as I said earlier, this session is on shock stiffness optimization, or in other words, we can say how shock stiffness affects your understeer gradient. So then we move on to the calculation for spring stiffness. We will see about a basic calculation for spring stiffness, which teams can follow. So then we will move on to the test and in IPG, and we will get the results from IPG control and discuss about the various types of results which you can get and what are the expected and what are the outcomes which you must avoid. Then we'll move on to yaw rate, which is a bonus concept in this session because yaw rate is being explained to let you know about derived quantities and IPG control. So without further delay, let's get into the session. So optimization of shock stiffness is generally done for two reasons. One is for ride and one is for handling. As you all know, ride is nothing but how your vehicle handles the undulations on the road. How much it is able to keep your driver or passenger comfortable. Handling is how much your vehicle is stable in a corner. So when going in corners, how much of the steering input is needed from the driver, how much is the steering effort from the driver. So these are all comes under handling characteristics. So what I have explained now is very basic terms of ride and handling, which a layman can understand. But when you speak in terms of engineering aspects, we have to define things with physical quantities like acceleration, velocity, radius, etc. Like some quantities must be there to define ride and handling so that we can characterize the vehicle. So a few parameters or parameters which are used for defining ride and handling are these two. Sorry, I didn't go into the slideshow mode. Okay. The parameters which are used for characterize ride and handling are ride rate and ride frequency for in case of ride, and yaw rate, understeer gradient, yaw damping ratio, transient response time, lateral stability margin for handling. So in this session, since we are going to focus on handling, we will take two parameters, that is understeer gradient and yaw rate in this session, and discuss about them in detail so that we can get to know more about how we can optimize handling using IPG. So first we will start with understeer gradient. Understeer gradient is nothing but a slope of plot between vehicle's wheel angle and lateral acceleration. To just put it in simple words. So the units used for understeer gradient is degrees per G. As I said earlier, it is the slope of plot between vehicle's wheel angle and lateral acceleration. The units is degrees per G. Since the vehicle's wheel angle is measured in terms of degrees and lateral acceleration is usually the SI unit for acceleration is meter per second square. But in this case, generally for automotive industries, we use it in terms of G. That is 1 G is equal to 9.81 meter per second square. So as I said earlier, it is one of the parameters to quantify vehicle handling. So to put it in other words, understeer gradient depends on how vehicle's wheel angle varies with lateral acceleration, right? Because it is a slope between vehicle's wheel angle and lateral acceleration. So vehicle understeer gradient basically depends on how the vehicle's wheel angle varies with lateral acceleration. As we have seen about the basic aspects of understeer gradient, let's get into a little deep and let us know why vehicle's wheel angle and lateral acceleration are being chosen. So there are several other parameters which can be chosen to define understeer gradient, but vehicle's wheel angle and lateral acceleration are chosen. Why is it so? Let me explain this with a basic real life example. When you give a vehicle to a driver, what he will do? He will just try to drive the vehicle in a straight line for slow speeds. Then he will gain some speed. Then he will try to make slow speed turns with larger turn radius. Then he will try to carry more speed into the same radius of turn. Then he will try to make sharper turns with more speed. So basically what we are doing is varying the velocity of the vehicle, radius of the turn, and according to the situation, the driver inputs the steering wheel angle, which controls the angle at which your front wheels turn. That is the wheel angle. So basically vehicle handling is nothing but how much your driver is working or how much is the driver input for a particular scenario. So to so it is very like people can understand this in a very different way. Different people can understand this in a different way. So to standardize this, they have introduced the lateral acceleration and wheel angle, so that all these parameters such as vehicle's velocity, radius of the turn, and wheel angle are all considered. So yeah, this is what about understeer gradient. So I will just uh, let, let you see this graph, which is usually obtained from a constant radius test. It is just an ideal graph. It is not necessary that your graph must look like this or so. It will vary for different vehicles. It will vary for different vehicle models as well. So as you can see in the graph, but I will just let you know what is understeer and oversteer from this graph. So as you can see, let me switch on to the pointer. So as you can see, as the lateral acceleration is increasing, or let's say for this example, I'm considering the radius of the turn to be constant. So as lateral acceleration is increasing, the velocity must increase, right? Velocity is the only term which can increase lateral acceleration if r is constant. As vehicle's velocity is increasing, as I said, the radius of the turn is constant and it is following, say, a circular path. So how much is the driver's input as the vehicle's velocity increases? So for example, if the in y-axis we have the steering angle or steering ratio. So let's consider steering angle for this example. So how much is the steering angle of the driver as the velocity of the vehicle is increasing? So if we have to give a more magnitude of steering angle, it means that the vehicle is not going in the intended path of the driver. So we say that the vehicle is understeering. Like vehicle is not turning as much as the driver wants. So then comes the oversteer part. Here, as you can see, after initially the steering angle has to increase for any of the vehicles, right? Because it can be the opposite. So as the steering angle increases over a certain velocity, the curve flattens and the steering angle starts to decrease. That means the driver is steering it in the opposite direction. Okay, the driver is steering it in the opposite direction so that the steering angle is actually decreasing. So this means that the vehicle is following a sharper turn and he is reducing the steering angle to make the vehicle stable. So this is what you can get from an understeer gradient plot. So moving on further, let's get a bit technical because what I have explained in layman terms, so that people can get the taste of the session. So another concept behind vehicle making a turn is the slip angle, because it is a very important concept. This is because of which the vehicle actually turns. To know more about slip angle, we have to get into the tire contact patch of the tire. Okay. So when the vehicle is static and you turn the steering wheel, what happens? The tire contact patch faces a resistance because of the friction between road and the tire, and the deformation at the tire contact patch is very less, as you can see. The treads are pointing in the initial direction. That is when the vehicle is static. So when you turn the tires, they except the tire contact patch, all the parts of the tire deflects, right? So this is what a deflection of a tire looks like when we turn the steering wheel. The same is shown in this picture as well, but in a more exaggerated way. As you can see, as the steering wheel is turned, the wheel turns, the tire contact patch gets deflected as shown in this figure. And let's say I assume a point somewhere on the tire, which is not at the tire contact patch. Okay. So when I move the vehicle, the tire rotates, and when this contact patch comes onto this, when the point that I assume comes onto the tire contact patch, since it is pointing in this direction, sorry, so since it is pointing in this direction, the vehicle will tend to turn in this direction. This is what is shown here as a path of the car. Okay. So let's say that I'm inputting a constant steering wheel angle and I'm increasing the velocity of the vehicle constantly. What happens? Your lateral acceleration increases. This lateral acceleration has to be provided from the friction between the tires and the ground, right? Because this is what is basic physics is. The centripetal force or the centripetal lateral acceleration has to be provided by the frictional force so that you can make a turn without slipping, sliding, or etc. So as the velocity increases and lateral acceleration increases, the tire deforms, deformation of the tire increases and the slip angle increases. So in other terms, I can say that to get more cornering force or lateral force to push the vehicle at a more speed into a corner, I need more slip angle. But this is true only to a certain extent, because for most of the tires, this is how the lateral force varies with slip angle. Okay, so as we say that as lateral force must increase with slip angle, yes, it does. It increase up until a point when the lateral force reaches a maximum, and it starts to decrease after that, right? So the skill of the driver is to maintain the tires at the optimal slip angle range so that he can get the maximum lateral force and can push his vehicle at a higher speed into the corners. So another interesting aspect in this graph is that as the as the vertical load on the wheel changes, this plot varies. As you can see, when the load is 4,000 on the 4,000 newtons, when 4,000 newtons of vertical load is applied on the wheel, the graph is like this. The peak lateral force is something around 4,500 newtons. So when the load increases, that is when it goes to 6,000 or 8,000, the peak lateral force increases, and also the peak lateral force corresponds to some other slip angle. Okay, as you can see, this dotted black line represents that only. So to put in simple terms, the vertical load on the tire also affects your cornering force, which in turn affects your vehicle stability during a turn. So once. So to put it in other words, any design factor that influences the cornering force developed at a wheel will have a direct effect on the directional response, because here load is one of the load raised due to the load transfer is one of the parameters because of which your lateral force is varying. There are several other parameters which controls your cornering force when you corner, and this affects your ability of the tire to achieve the cornering force as well. So we will see about this in detail in the next slide. Again. Is my slide changing?
No, Kamal. Can you just come out of the slideshow?
Okay. Is it visible? It is changing up. So as I said earlier,
just a minute, Kamal. Your screen is not visible. I think you stopped sharing.
sorry, is my screen visible now?
Yeah. It's
Okay. Sorry for the disturbance. Yeah. As I said, whatever the design factor or vehicle factor which is going to affect your cornering force developed in each of your wheels, it will have a direct effect on your directional response of the vehicle, as I said in the previous slide. So some of the parameters or design factors which will affect your cornering force is these parameters listed here. So these parameters are generally called as understeer gradient arising because of the tire cornering stiffness, because of camber thrust, roll steer, etc. So before going on to this, I will just tell about this equation, which is a very basic equation which is derived from a bicycle model. So there are several assumptions going into this because to make it simplified. So you cannot use this formula directly to calculate the understeer gradient of your vehicle. But what you can do is calculate these parameters and see how it is what are the values of these parameters, and can come to a conclusion that your vehicle is understeering or not, understeering, oversteering, or what is the kind of vehicle handling you are getting. So to make life simpler, we can directly get the understeer gradient value using IPG, and get the plots necessary to get the understeer gradient. So before going on to the next slide, I will just explain about these individual factors a little bit, so that you can get a brief idea about this one. So first is the tire cornering stiffness. The understeer gradient arising due to tire cornering stiffness depends on the uh, vehicle's weight in the front axle and the rear axle, and the cornering stiffness of the tires. Okay, as you can expect from this term, tire cornering stiffness. This is the understeer gradient arising from the stiffness of the tire. So next is the camber thrust. Because when your vehicle goes in a corner, the body tends to roll, right? Because of that roll, camber is generated in the inside and outside wheels. Because of that camber, there will be a force called camber thrust. Usually this camber thrust acts in the direction of lateral force, and it's very negligible compared to the lateral force. But still, it is one of the parameters or lower level parameter which affects your understeer gradient. So to know more about these parameters, you can refer to Fundamentals of Vehicle Dynamics book in the steady state cornering chapter, so that you can get an in-depth view of these parameters. Because each of these parameters, if it is explained in this session, it will go for a long time. So then comes the roll steer. Here the epsilon f and epsilon r are the your coefficient of roll. That is how much toe angle your wheels at the front and the rear experience for 1 degree of roll. So these are these two coefficients, and d phi by dya is the roll gradient of your vehicle. Here too, dou phi by dou ay is your roll gradient of your vehicle. That is, phi is the roll angle and ay is your lateral acceleration. Don't get complicated because of these things. We will see about roll gradient in IPG as well. So yeah. So next is the lateral force compliance here. This arises because of the lateral forces acting on your wheels. When your vehicle goes in a corner, as I said, the wheels and the suspension arms experience the lateral force. Because of the lateral force, your suspension arms and geometry might deflect according to the stiffness in the bushings used. So a gradient arising from this factor is called as lateral force compliance here. Okay, yeah. Yeah. So next is the aligning torque. This is actually different from all other parameters, which I will explain why. So before explaining that, I want to make one thing clear about the remaining parameters. That is the parameters except aligning torque. As you can see in each of these terms, you can see a parameter explaining the front axle or front suspension at the like it is this term explains about the front axle or considers the front suspension system. Then it considers the rear suspension system. As you can see, the C gamma R divided by C alpha R. So this is nothing but the camber change per degree of roll, and C alpha R is the tire cornering stiffness. Okay. So in all these terms, it is like that only. Here we see that the cornering stiffness of the front wheels is used in this term. It is the rear suspension systems parameters are used. Here too, the epsilon for F is for front suspension and it is for rear suspension. Here too, it is the same. And here also you will get, I will see that like these are parameters calculated for front suspension is subtracted, is getting subtracted by the parameters calculated for the rear suspension. So what basically here is your vehicle's handling, that is understeer, oversteer, or neutral steer, depends on how these parameters is distributed among the front and rear suspensions of your vehicle. If your rear, so basically there's a thumb rule that if your rear suspension is more compliant than your front suspension, that is your rear suspension system is stiffer and than your front suspension, the vehicle tends to oversteer. And when your front suspension is more compliant or stiffer than your rear suspension, the vehicle tends to understeer. So these are some of the parameters. So then now I will come on why aligning torque is a different one, because aligning torque, as you can see, there is no difference. We are adding two parameters. There is no difference here, because of which it always tends to understeer. Like if you reduce the aligning torque, you are making the vehicle tend to oversteer. If it is getting increased, it will understeer. So this value won't be negative, but other parameters can be negative. So next is the lateral load transfer. This parameter talks about how your roll moment is distributed. How is your roll moment on the front and the rear? These two parameters explain that only. These two parameters explain those. So I hope you would have gotten like a basic understanding of understeer gradient, the theoretical aspects behind that, and basic understanding of how these models are being developed, like, and the books to refer to. So next we'll move on to the load case, which is being used to actually validate this understeer gradient or get this understeer gradient data. So a most common load case or testing scenario that is being used is the constant radius cornering test. ISO 4138 is the ISO standard followed for this test, and this is because you have to standardize the testing parameter, right? Because I may get a different value of understeer gradient if I test the vehicle in a different condition. So to standardize all this, the ISO standards is being introduced. And for our case, for our virtual dynamic event presentation, the teams must understand this definition of constant radius cornering. That is, the steady increase in velocity until either the lateral acceleration reaches 0.6 g, the vehicle rolls over, or the vehicle starts to slide, whichever occurs first. So what it means that the vehicle's velocity must rise steadily following a constant radius path until the vehicle reaches acceleration of 0.6 g, or the vehicle rolls or the vehicle slides. So whichever comes first, the simulation must stop. Of course, when the vehicle rolls over, the simulation will stop because of the error. So we will define. So we need an end condition to define that the simulation must stop at 0.60, which we will be seeing in the IPG window soon. So these are basically the input parameters, that is turning radius 60 meters, longitudinal maneuver taken care by the manual pedals, and the lateral maneuver is given as not specified, because if you give it as IPG driver, the IPG driver will restrict the vehicle according to the parameter which you have given in the driver parameter. So this is what. Then these are some of the output plots that has to be shared in the presentation to make it clear to the judges how we have validated the vehicle. And these are the output parameters which you can get from this plots. So front and rear roll steer alone will not be like calculated from this test case. It can be, but it can be calculated from your KNC data. So you can directly mention the value there. Okay. So these are some of the steps that has to be followed. Let me quickly go into IPG window and I will show how to actually like load the test case in your model. So first of all, go on to project folder and select your project folder. Then what I would say is go to the product example. Like there will be a product example by default in IPG, where there will be several test cases there. So go to vehicle dynamics, go to handling, then there will be a test case called as steady state circle of 42 meters. So what they're saying by 42 meters is the radius of the track in this case is 42 meters. But in our case, we have defined it to be 30 meters. So we have to edit the track. Okay. So I will just open it. So as you can see, some other vehicle model is getting opened. So I will go to the track window to track, and I will save this track in my project folder so that I can edit and create a test run in my project folder. Okay. So what you have to do is click save as, go to your project, test team ID underscore team name road, There you can go and save your track. Okay. What you're doing is opening test run from a default test run. You are taking the track alone and saving it in your project folder. So okay, I will just type it as underscore trial and I will save it. Now the track has been saved in my project folder. So I can close this window and I will go to the test case which I have. Okay. Or let's say, let's make create a new test case. So I have to select the car now. And I will select this one. Okay. Go to scenario or road. Here, as I said, I have saved it in my project folder. Now I can load the road file here. As you can see, I typed it as circle underscore 42 meters underscore trial. Now it's visible here. So you can click OK, the track will get loaded. So how to modify the track? That's what we are going to see now. So first of all, click on this road tab, road segment tab, and delete this straight line segment, because we are not going to accelerate the car in a straight line and introduce into a turn. We are going to maintain a constant delay starting from the circle turn itself. So we can delete that. Now next we have to modify the radius of the track, right? So for that you can click on the track, go to parameters here and change your radius 30 meters. So the track is getting smaller as the radius is decreased. So another thing is your friction coefficient, right? Yeah, here is your friction. Since it is mentioned as 0.7 in the rule book, you have to enter 0.7. Okay. So we have modified the track and made a track which is needed for our test case, right? So now we can save this, save as with a different name in the same road folder, so that we can use it for our test runs. I will save it as 30 meters underscore trial. Okay. So I have now saved the track alone and modified the track and saved it in my project folder. So this is what I have to do. Then let's go on to the maneuver window. In maneuver window, before going on to that, we must specify the route which the vehicle is going to follow. The yellow box here shows the point where your vehicle is going to start from during the simulation. So it is in the correct position. So I will click on this route selection and I will select the route in which the vehicle has to follow. So this is the circular path which the vehicle has to follow. Okay. So let's move on to the maneuver window now. In the maneuver window, maneuver is for CRC test load cases pretty simple, because there is only one maneuver and one end condition, that is 0.60. So first of all, define the end condition. It is defined as absolute in bracket type car dot AY, because it is the user accessible quantity defined by IPG greater than or equal to 5.886. That is 0.6 G when converted to meter per second square comes as 5.886. That's why I have defined it like that. So your absolute means like a modulus. Even if the value is negative, the computer won't consider it. Okay, just to make sure that no errors are occurring. So absolute is to is to create a modulus for the value. Then car.ay is your lateral acceleration UIQ. So this is fine. Then we will go to the longitudinal maneuver, where you will give manual pedals with a throttle of 1. Okay. Then for MBAHA vehicles, the gear has to be selected as 1. For EBAHA vehicles, it's not necessary. So for safer side, I will give it as 1 here as well. So then comes your lateral dynamics, right? In lateral dynamics, as I said earlier, you can give it as not specified. Okay. So I have loaded the track, selected the route, given the maneuver, etc. So I guess now I've also selected the vehicle here. So I guess now I can run the simulation. I'll go to IPG movie and show the simulation. As you can see, the vehicle's velocity is steadily increasing as it follows a constant radius path. Here is a GG diagram showing the lateral acceleration. Okay. GG diagram showing the lateral acceleration. So for the training purpose, we have already created test runs for the for explaining optimization of shock stiffness as well. So I will open those test cases and I will run those one. So I will load this one. Okay. So let's now start it. As you can see, when the vehicle reaches a lateral acceleration of 5.89, the simulation is getting stopped, right? As we have defined in the end condition here. 1 second. In the maneuver window, we have defined the end condition as greater than 5.886. When the lateral acceleration reaches greater than 5.886, the simulation is getting stopped. So let me quickly go on to the shock stiffness calculation now, because our entire scope of this session is on shock stiffness optimization, or in other words, how shock stiffness affects your vehicle handling, right? So before going on to this session, I want to give a disclaimer or a note that this is a very basic calculations to get a shock stiffness value to start with. Teams can also use your shock stiffness value or data which you are getting from your shock supplier, etc. So this is just a rudimentary calculation, right? Okay. So yeah. Also, the values which we are showing in this slide are the numerical values is just for reference purposes, just to show in this slide, or for just for this session. So teams are always required to do the calculation on their side and perform the simulations. So here is the basic shock stiffness calculation. So this is like a basic assumption which is made the first step. That is, for passenger cars, the ride frequency is around 0.5 to 1 hertz. For rally cars, it is 1.5 to 2 hertz, right? So our vehicle is an off-road vehicle and comes somewhere in between passenger and rally cars. So it is up to the teams to assume whatever ride frequency they want, because these things are shown just for references, and this is just like a standard thing which is being followed. So step one is assume your ride frequency. So your teams can assume your ride frequency as per your interest, which as a units of hertz. From that, you can calculate your angular frequency by multiplying it with 2 pi. Then which will give a value in the terms of radians per second. Then when you come to ride rate, this is the formula for ride rate. We know mf, that is mass on a particular wheel. From these calculations, we can get the mass distribution on front and rear axle. Then from this, you can divide this value by 2 to get a mass on a particular wheel, either at front or rear. So mf is known, kr is not known. We have to find kr, and omega r is known from this data. So then comes the finding of wheel rate. So wheel rate's formula is this one, where we require ride rate, tire rate, and your these are the two parameters that is required for finding wheel rate. So as I said, ride rate is found from here. Tire rate is a tire stiffness that is expressed in Newton per mm or Newton per meter. Okay, not cornering stiffness but tire stiffness. So then comes your spring rate. So based on the motion ratio and the inclination in which your shock is being mounted onto your arms, control arms, this spring rate varies. We have found the KW, KS is to be found, KW is found. So from motion ratio and angle A is known. So from this we can find a spring rate. So this is as I said earlier, these values are for representational purpose only, and teams have to perform calculations according to the design. And we are not responsible for any kind of we are not responsible for these values. So this is just for representational purposes. So for this vehicle, the mass on each front tire comes out to be 50 kgs, on rear tires it comes to be 64. So whatever I said here is done in Excel, and it is pasted here as a photo to calculate the spring rate. It comes to be 22,065 for front and 26,019 for the rear. Okay. So we will now move on to IPG and see how shock stiffness actually varies your understeer gradient, and also plot these graphs which are need to be shared in the presentation. So first of all, I will plot all these graphs which are need to be presented, and then I will move on to the shock stiffness case. So this is your IPG control graphical user interface, which was explained earlier. So yeah, y-axis. I will close it. Just getting hand. I'm sorry for the delay. I guess there is some issue with this, my PC. Okay. My project folder is loaded, and I will open the test case. Case one. Okay. I'll go to file IPG movie. I'll file IPG control as well. So yeah, this is the user interface. Also, when you open IPG for the first time after closing, you have to run the simulation once to get any data in your data in your IPG control. So I will first of all start the simulation, run it for one time. Yeah, now the connection has been established between IPG controller and the simulation window. So we can now add few diagrams and plot it in a single simulation. So first thing I will do is plot car 2 in the y-axis FL, then AY will plot, sorry, just will plot in the x-axis. I will delete that. This is usually for understeer gradient, you have to take the average of front wheel to angle and right wheel to angle, right? So as I said, it is a plot between the wheel angle and the lateral acceleration, right? So for this wheel angle, the inside wheel and outside wheel will turn at a different angle because we don't follow parallel geometry. For parallel geometry, it will be same, but for Ackermann or anti-Ackermann, it will be different, right? So you have to take a average of the two values to get your understeer gradient. So which you can do it in the Excel by exporting this data. So for now, I will just show how the graph varies and how the parameters are getting plotted. So in the y-axis, I will add a FR as well. Then here is a steering wheel angle gradient for dot y. So next is your roll gradient. Yeah, I have set the parameters which needs to be plotted, and I'm going to run the simulation again. So as you can see, the values are getting plotted. Yeah. So the plot seems to be pretty much okay. There is no much deflections or like that. So this is fine. So as I said earlier, you can export to file, save it as an Excel, and let's choose the location which you want to save the Excel and rename the file, and you can click on save. So as explained earlier in the session. So before moving on to the data part which you are going to get from this plots, let's see few other vehicle models which are not optimized or which needs to be avoided, so that you can learn like a lessons from those models. So I will open those models and share it. Check. Yeah. Mm. As you can see, the values are like varying a lot, not a straight line or so. It is like the graph is getting messy. So as you can see, the vehicle is getting toppled and the simulation is stopped. Okay. These red pointers, as you can see here, are the wheel forces acting. Okay, in the vehicle on the vehicle's tire, and you can see as the speed increases, the vertical force is becoming zero, and the vehicle tends to topple. So these kind of vehicles must be optimized, and you must do a study on why is your vehicle getting toppled like that, and you have to optimize your vehicle model. Okay, shock stiffness is only one of the parameters because of which uh, your vehicle handling might get affected. There are also several other parameters such as your KNC, moment of inertia of your suspension parts, etc. So for the purpose of the session, we have selected only the shock stiffness setting, and we are doing the session. So let's look into why it is actually happening. What is the vehicle parameter that might cause this issue? When I go to suspension, they have said the vehicle model has a front suspension stiffness is higher than the rear suspension stiffness. But usually for because of ride frequency reasons and everything, the front suspension stiffness is lesser and the rear suspension is higher. Maybe this is one of the reasons why the vehicle is toppling. There might be other reasons also, such as lower track width, higher CG, etc., that is causing the toppling of vehicle. So like this, you can verify the parameters which you have inputted in the vehicle and can optimize your vehicle. This is just to show that there are parameters which can affect your vehicle, other parameters that can affect your vehicle handling. Then I will open another test run, using which I will show the wheel forces in the IPG control. Just getting loaded. Okay. For that, car.fz, let me, since it's a left hand corner, the right wheels are more stressed and it gets some more load. So let me see for right side front wheel. Yeah. So let me also change the x-axis to time. Okay. And start the simulation. As you can see the plot, it is like not at all linear, and it shows that the vehicle is not in the steady state. So as you can see, the vehicle's inner tires are almost loaded up until 720 newtons, right? Okay, let me plot the inner wheel force also to know how much, because it is almost zero. Yeah, with the Uh, as you can see, it is almost getting into 0 range. As you can see, it is 0. You can see the red color, right? So the vehicle is very pretty unstable, and it is in the transient or quasi-static state, and the vehicle is about to topple when if it goes beyond this limit of speed. So you can optimize this thing and present it to the judges on how you have changed the vehicle parameters and how IPG has been helpful in validating your vehicle. Okay. So let's now move on to the optimization of shock stiffness part. So we'll open this test run. Yeah. Let me have only 2FR. Okay. Let me have the steering angle and these two are not correct. So I will rather have car roll here. In the x-axis for roll gradient, we need to have lateral acceleration. So I'm choosing lateral acceleration here. So to see how a roll gradient is also varying with your shock stiffness. For that purpose, I'm plotting this graph. So yeah, so now let's run the simulation. Oh yeah, the plots have been made, and let's go into the shock stiffness parameter for this vehicle now. Parameters car _1 I'm choosing. So as you can see, the front stiffness is 22,000, the rear stiffness is 26,000. So as per the calculations here, as per the calculations we have done here, right? Actually, yeah, it must be 26,065. So I will say 26,065. So I have rounded it and I have entered as 22,000. So yeah, so 22,000 and 26,000. For this setup of shock stiffness, we are getting a plot like this, right? We are getting a plot like this. So what I will do is I will create a snapshot of this plot and compare it with another shock stiffness setting. So click on this down arrow button on the symbol and create snapshot from the current data. So it will just save the data which you ran earlier. So now let's open another test case. So in this test case, I have a different vehicle model. So not different vehicle model, same vehicle model with a different shock stiffness setting. As you can see, I have made the front suspension more softer, like 22 from 22,000 to 20,000, and I have increased the stiffness from 26,000 to 30,000 in the rear. Okay. So now let's see how this parameter change affects the vehicle handling with this plot. So as you can see, the maximum steering wheel angle is, sorry, the wheel angle is reduced. The same goes for steering wheel angle. The steering wheel angle is also reduced, and the flow or the rate of change of wheel angle or steering wheel angle with lateral acceleration has tend to decrease, right? So this is what is seen. So as I said earlier, when your front suspension is less compliant than your rear suspension, then it tends to oversteer, or when your front suspension stiffness is less than the suspension stiffness of your rear, then it tends to oversteer. So this is what we were like changing the shock stiffness and was setting up. So let's go into another model where the shock stiffness is changed from change. I hope teams are able to follow me. Yeah. So here I have I have fixed the front stiffness as 20,000 only, but I have kept the rear stiffness as 40,000, right? Okay, so I have just increased the stiffness of the rear suspension. So let's now see how it is affecting the vehicle's handling behavior. Oh yeah. Before that, I will create a snapshot. You have to click this C1 and create a snapshot, right? You can't create a snapshot from an already present snapshot. So snapshot from the current data, so that I can calculate all the three setups of the vehicle. We'll go to start. So as you can see, the slope of the graph has been reduced further. Has been reduced further, and the steering wheel, since this wheel angle has reduced, the steering wheel angle will obviously reduce. So as you can see here, the slope value is getting reduced. So I forgot to talk about the roll gradient. Yeah, as I am setting a what to say, a more soft stiffness, soft shock in the front, it tends to roll higher, right? So this is what about roll gradient. So roll gradient is pretty simple. It is a linear graph from which you can get data easily. So for this comparison purpose and to calculate how much the actual variation is the understeer gradient is by varying the shock stiffness, I have already exported this data and I have done the post processing in the Excel, and I have calculated the data. So I will just open the Excel sheet and show you. So this is what we have got in the IPG driver as well, right? So IPG control as well, right? So this is what I have got from the IPG control, and I have plotted this one. This is before post processing. So this is after post processing. So let me explain what I have done here clearly. So yeah, so as you can see, the slope is varying. First, it seems to be linear up until this point. Then after some amount of lateral acceleration is getting gained, the slope is varying. The slope here and here is not the same, right? The slope is greater here, then it has reduced here. Then after that, some amount of increase in the gradient has increase in the slope has been found, and the simulation is stopped at 0.6 of lateral acceleration. So for in this case, I can't take the average value of slopes, right? Because it is like varying too much and the difference between them is high. So taking average is not a good idea. So what we can do is you can get the data for a particular range of lateral acceleration. For example, I can delete those datas in the y column that corresponds to lateral acceleration less than 1 and greater than 4. So I will put it in other words. I can get the slope of this plot for x between 1 and 4. That is, I will delete those datas for which lateral acceleration is greater than 4 and less than 1, and I will get this region alone. Get this region alone, and I will plot a trend line and get the slope data. Okay. So as I said earlier, it has to be done for both front left wheels and front right wheels, because the angle in which both are turning will be different, and I have to get an average value. So this is what I have done here. So first sheet shows, as you can see, I have deleted those data corresponding to lateral acceleration less than 1 and greater than 4. And here I have plotted the front left wheel angle here. Okay, sorry, front right wheel angle here. Front right wheel angle here. And I have plotted the trend lines, and I've got the slope for these graphs. So because of the units used here, it is in degrees per meter per second square, because IPG does not allow to use G as a unit. So we have to convert it into degrees per G, right? So what I have done is I have used the formulas to multiply it by 9.81 so that I can convert the units to degrees per G. So 0.6325 is the slope or the gradient. So I have multiplied it with 9.81 to get the value in degrees per G. So this is what I have done for all the three setups, all three shock setups. And as you can see, I have almost reduced the understeer gradient by 1. I have almost reduced the value of understeer gradient from 6.2 to 5.2 by changing this shock stiffness or by optimizing it. So it is up to the teams to to know. It is up to the teams to decide what kind of understeer gradient value they want. So for usually for passenger vehicles, it is around the value of 2 to 7, 2 to 5 or 2 to 7. So it is up to the teams to design the vehicle according to their intention, whether to make the vehicle understeer, oversteer, etc. So, but your graphs or plot must be like proper. So as I will show some plots which are not like ideal or which needs to be avoided. These kind of variations must be avoided. Okay, these kind of abrupt variations in the plot must be avoided. So yeah, this is what is shown here also. So these must be avoided. These kind of disturbances can be handled, but these kind of abrupt changes and scribbling like plot cannot be accepted. Like this must be avoided, and you must optimize your vehicle. If this is your plot for your vehicle, then vehicle model, then there is something wrong with your vehicle. Either you are manipulating it or not entering the correct values. Okay. I will get back to that Excel sheet. Yeah. So this is what I got for got from the IPG control and did the post processing, and this is what the value I got. Okay. So for front right also similar plot has been made. It comes under the negative area because of the sign conventions. The wheel angle is negative for right wheels. Sorry, for the left wheels. So here I have got the similar like I have plotted the similar trend lines like for this graph, and have converted the units so that I can get the data for inner wheel as well. That is yeah. So now we will take the average of these two values, right? So this is the average of these two values. I have calculated the average of these two values and have reduced the understeer gradient from 5.6 to 4.8. Okay. So the outer wheels are of more concern to us because it is taking up the much load, but 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 in a standardized way, we have to take average of both both the understeer gradient value which you have obtained for front right wheel and left wheel, and get an calculate an average of these and present it to the judges. And also one thing which you can do is you can show this Excel graph and show that this value is being like we have got this value for a lateral acceleration range of 1 to 4 meter per second square. You can also add that so that judges can get a clear view of this. You can add the plot from the IPG control, add plot after post processing done is done in Excel. Then you can also get specify the values and the lateral acceleration for which you have obtained these values, right? So that it's made clear to the judges. So So another plot which has to be plotted in the IPG control is the steering wheel torque. So that can also be plotted. This is the steering torque. Oh, sorry. Yeah, this is the I added in the IPG control. Let me delete this diagram so that it's clear for you guys. So, yeah. I will start the simulation again. This is the plot for steering torque as the simulation goes on and the steering wheel angle increases, the steering torque also increases. So yeah, this is just to let you know what are the UAQ that is being used for getting outputs of the CRC test. Okay, then we will move on to the last topic, that is yaw rate and yaw rate gain. So yaw rate is actually the speed at which the vehicle is rotating about the axis perpendicular to the ground and passing through the CG of the vehicle. Okay, it is basically the speed at which your vehicle is rotating to make a turn. So obviously it is measured in terms of radians per second, or it can be measured in terms of degrees per second also. So to characterize the vehicle handling, yaw velocity gain is usually yaw velocity gain is usually plotted with the speed of the vehicle. Okay. So what I have defined in here, uh, is the definition for yaw rate, not yaw rate gain. You must understand that yaw rate gain is different from yaw rate. So let me go into yaw rate gain now. Yaw rate gain is simply the yaw rate gained by the vehicle for a unit angle of wheel angle. Okay. So how much is the gain in yaw rate for when I turn the wheel by one angle? So this is what is yaw rate gain is. So obviously yaw rate gain will be defined as yaw rate divided by the wheel angle. Here wheel angle has to be the average of your front left toe angle and front right toe angle, so that you can get the overall picture, not on the one side of the vehicle. Yeah. So let me plot this graph in IPG control as well, so that using the user derived quantities, because it cannot be like it is not yaw rate gain. Yaw rate is an user accessible quantity, but yaw rate gain is not an user accessible quantity. So let me go into the IPG window and let me show you that. Yeah, IPG control. So I will have this plot here, so I can clear these snapshots so that it's clear. Yeah, I will have this. Okay. So let me first get into let you know how to get into this user derived quantities. So click on this plus symbol and drag it slightly. So then the drop down will open and you will get four options. That is data from file, online connection, calculated signal, and snapshot. So here you have to get calculated signals. That means that that you are that you are getting a parameter which is getting calculated from an already present UIQ. Okay. So this is why it is called as a calculated signal. You can do mathematical operations to calculate the signal. So I will add a user accessible quantity, sorry, user defined quantity, that UQ. So I will define it as yaw rate gain. Okay. These names can be defined by you. It can be anything like that. So this is where you have to be a bit careful in the definition part. So you have to first enter C1, that is the key for connection between the IPG controller and the simulation window. So select C1, then type 2:. When you type 2:, automatically all the user accessible quantities will be shown as a drop down. Then go to yaw rate. I have yaw rate, right? Yaw rate is already there. Yaw rate gain is not there. I will select yaw rate and I will divide it with divide it with again when yeah, I will mention this as well. So I am going to divide it with another user accessible quantity, right? When you are calling another user accessible quantity, also you have to define this C1 syntax kind of thing. So 2:, and you have to according to the formula, it is divided by the wheel angle, right? So for this case, I will take the toe angle of the front right tire and see how the plot goes. Sorry. Dot. So yeah. So I have defined the user accessible quantity. So I will save it. So I am able to see the user accessible quantity. I will click this graph once, go to Y and create yaw rate gain. So as you can see, it is saying that could not add quantity yaw rate gain. Dataset does not include required reference quantity. Okay, what it says is, I will get into this as well. So when I defined the yaw rate gain, I divided the yaw rate with the toe angle of the front right wheels, right? So what I have to do is I have to plot another graph which has the user accessible quantity there. because it will take data from the already present user accessible quantities and will take it here to the graph and calculate it. So what I have to do is I have to simply add a graph or plot the car yaw rate in this graph as well. So yeah, car dot yaw rate. So I am adding yaw rate in this graph. Okay. So now when I go to this graph and select on this, it is again showing that once again I will delete this and create a new one because I will first of all add those user accessible quantities and come to this graph. I have got the yaw rate here and I will go to this one. Yaw rate C1 or dot yaw rate divided with C1 colon to F R. So yeah, it is showing like that because the x added r.ay, right? In user-defined quantity graphs, the x-axis should also be plotted from this table, right? I cannot choose car.ay from the user accessible quantity, and on the y-axis I cannot define the user-defined quantity. So both x and y-axis should be a user-defined quantity. So that's why it is getting this error. So I will go to x-axis and I will select time instead. Okay. So then I will go to y-axis and choose this yaw rate gain. Now it is getting plotted, right? So now we will run the simulation and see how the yaw rate gain actually varies. So yeah, this is the plot of yaw rate gain. One second. You can go to right click and edit quantity to edit the data. So yeah, I have plotted it with yaw rate divided by the car tow FR. Okay. So yeah, so this is how you can derive a user defined quantities. And also one thing you can do is in this definition also edit quantity. In this definition, you can also refer to another user accessible quantity, which I will try to do it now. Okay. So I will delete this one. So what I will do is first calculate the average of the two angles, then I will calculate the yaw rate gain. Okay. So here I will create another average angle I will define. So yes, P1 dot 2 plus or right. Okay. So I will calculate the average of this. You must be clear with the syntax because if you make any error, the user defined quantity won't be plotted. Okay, I will save this one. So in this graph, I have to add to FL as well because it is being used by the user defined quantity, right? I will go to FL. Plotted that one as well. So here I will x-axis time and then the y-axis I will get average angle. So I will plot it now. So yeah. So I have calculated the average value of two angle for this case as well. When you change the units here, the values will get automatically changed here as well. Once again. When you go and change the units to degrees here, the values will get automatically updated. You need not worry about that. Okay. So now what I will do is I will use this average angle to like define the yaw rate gain. Okay. So I will click on this and define yaw rate gain 2. Then I will move on to C1 car dot yaw rate. Then I will divide it with here. Since I am going to refer it to a user defined quantity, instead of C1 you have to give it as UQ. Okay. U capital Q, then it is coming automatically. Then it will specify all the parameters which you have defined. I will click on the average angle. So yeah, everything is fine. Units also you not give if it is already if it is present in this drop down, you can give it, otherwise it's not necessary. Then you can save it, and I will plot this one in the graph now. So in the y-axis I will add a yaw rate gain. Then the x-axis I will select time. It is already selected, so no problem. So yeah, I will start. So as you can see, the yaw rate gain is being plotted. Yeah, it is going in the negative direction because of the sign convention. Since the car is rotating towards the left or taking a left turn, the yaw is towards the left, that is in the anti-clockwise direction. So the sign convention is left. So the you can get the slope of the graph and define yaw rate gain. So actually, yaw rate gain will be theoretically covered more in the upcoming session in the next load cases. So yeah, this is with my session. Hope you all have a great time in my session. Hope you got the idea of optimizing shock stiffness and theoretical idea about understeer gradient and user-defined quantities in IPG control and how to load the load case and start the simulation, etc. So hope you had a great time. So yeah, thank you for attending this session.
Yeah, thank you, Kamal. Thank you for that very detailed session. Also explaining the theory aspect as well. So we'll just quickly start with the next session and not delay much. So Samprit, are you ready? So the next session we will have is with on center. And yeah, Samprit, please take us through for the next session.
Yeah, my screen is visible, right?
Yes,
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 yes.
Yeah, thank you. Yeah, so good afternoon to one and all. And my name is Samprit, and in this session, we'll be talking about the on-center test load case. First go through the respective agendas that we'll be covering in this session, will be including with respect to the introduction to on-center test, where we will get to know about what is on-center test and why on-center test needs to be used. And we'll then go through the ISO standard for on-center test load case. And after that, we'll know about the load case definition with respect to on-center test, and later we'll understand the behavior of yaw and roll gain characteristics for an automotive vehicle and also for an ideal behavior of a vehicle. And then we'll go with the lateral dynamics driver model with respect to on-center test. And once we finish that, we'll get into the load case manual commands that we need to have in this on-center test load case. And after that, we'll understand the factors that are affecting the handling characteristics, and later we'll have the results and discussion. So first, let me start with the on-center test. So what is on-center test? It is a critical assessment wherein which you will assess the vehicle's steering performance at a very smaller steer angles near a straight ahead position given by the driver input. And It determines that how well the vehicle maintains its stability as well as the control during the minimum steering inputs that is being provided. Since driving during straight track conditions, the vehicle's top speed requires only small steer adjustment of steering wheel input. So to keep the vehicle in the center, so this on-center test comes into consideration. So let's understand what stability and control with an example. So visualize yourself sitting in a car and you are driving the vehicle at a highway with respect to the high speed, and in order to have the terms stability and control, what does it mean? So when you are driving, you will try to maneuver your steer, so in order to put your vehicle in a center position of the lane. So if in case you do not handle the steer, it will either tend to the left or right, and the tendency of moving of steering angle happens. So in order to control that, so you will try to position your steering input such that you keep your vehicle in the center position. So that comes under control. And the stability is the small steer inputs that you provide. So in order to get back to your original position, you try to steer the input, steer the steering wheel. So when you do that, so the transition of the steering wheel angle to its original position needs to be smooth. So how well the smooth transition is to come back to its original position is the characteristics that explains about the stability of the vehicle. Let's also understand another example where in which why on-center test is required. So the on-center test, so if you are driving a vehicle in a event, so in a racetrack, so you are, in order to compete you need to have more number of lap times, so you compete for lap times, and also in order to have those more laps, you will count up faster laps with faster speed of the vehicle. While doing that, you while doing that, what you requires is the vehicle's handling predictability. What does it means the how well the vehicle inputs are been understood by the driver. So the driver needs to know how the behavior of the vehicle is. So that comes under the handling predictability. So in consideration with those, let's go through these videos for just understanding of what are the technical forces that counters while you are steering the steering wheel. When you are going in a straight ahead position, so you will encounter a corner. When you try to steer, so you will have a force which is called as a centrifugal force that is acting on the vehicle. So this centrifugal force tends to keep the vehicle in the straight on position, and you require more power in order to overcome this. And also the contributing forces are the rotational forces that are created due to the tire rotation, as well as the vehicle is having other parameters like the tire forces that are acting on the vehicle. That all comes into consideration. The suspension parameters, the vehicle chassis, all comes into consideration. So when you steer the steer input, so what force that you generate is a rotary momentum that is created by the steering wheel input, and this rotary momentum is transferred via the linkage, as you can see over in this video representation, and it is further transferred to the tires, and due to that condition the back forces are generated, and it is also tending back to the vehicle, and also the tire forces, as I mentioned, are also acting on the vehicle. So these are some complex effects of all these forces are added together, needs to be dealt by the interplay of the steering system that we counter, and it includes this handling predictability needs to be understood by the driver. So that's why this on-center test is performed. Yeah, now as we understood why and what on-center test is, let's next go with the ISO standard. So we have ISO standard for on-center test, which is 13674, which speaks about the method to assess the response of the steering as well as the stability of the vehicle when the small steering wheel inputs are provided. So the key parameters that are included in this ISO standards are the steering angle response, yaw rate, as well as the lateral acceleration. And the testing consideration includes the vehicle is driven at a steady speed condition and will have a small amplitude steering inputs which are applied in order to evaluate the response of the vehicle. Now we'll understand the load case definition that we'll be considering for the on-center test load case. So for this load case, we'll be having a steady state increase in velocity until the desired speed is reached. Like the speeds are simulated for 30 kmph and 50 kmph respectively. And the steering wheel input should be such that a sinusoidal signal needs to be considered with 0.2 Hz frequency and such and enough amplitude to generate 0.2 g of lateral acceleration, and the velocity should be controlled by a IPG driver and there should be no braking involved. So I will be explaining further in detail about these input commands, and the output plots that needs to be considered are the yaw gain, roll gain, and steering wheel angle versus steering wheel torque, and steering wheel torque versus lateral acceleration, as well as the lateral acceleration versus time. Now, as we consider that yaw gain and the roll gain, so what does it actually means and the how the behavior is there with respect to graphical consideration. So here we have two behavior models. One is for, like, you can at the left you can see it's a model of a yaw rate versus steering wheel angle, or the roll versus steering angle for an automotive vehicle. So this behavior that you can see for an automotive vehicle, and in the right you can see like the plot of roll versus steering wheel angle, which is an ideal behavior for a BAJA vehicle. So to let you know about the dynamics of this, so we'll just understand about the yaw rate and the yaw rate versus the steering wheel angle. So in automotive dynamics, when we are particularly analyzing the on-center test, so the relationship between the yaw rate versus the steering wheel angle is very critical. And what should we expect from this on-center test is the yaw rate represents the rotational velocity of the vehicle and about its vertical axis, and it indicates how fast the vehicle is turning. And the unit that's typically measured for the yaw rate is radians per second or the degrees per second. And for the roll, it is in degrees. And particularly for the steering wheel angle, it refers to the angular position that you are providing for the steering wheel from its center position. And the unit for the steering wheel angle is in degrees. And in this graph, you can see the typical linear nature of the graph, and for smaller steering inputs, how the yaw rate response is, you can see over in this graph. And the slope that we are considering over here, it indicates the vehicle responsiveness. As you can see, the red dotted line over here, it represents the slope of the graph, and it tells you about the how vehicle responsiveness is. And we can have three considerations in this slope. In this slope consideration, one is a steep slope, or a shallow slope, or a zero crossing. What does it mean? Actually, is the steep slope will be having more responsive vehicle, wherein which for smaller steering inputs, you will have a significant changes in yaw rate. So the graph that you are seeing will be having a significant changes in terms of yaw rate for a smaller steering wheel inputs. And if in case you consider for a steep slope, so for a smaller steering input, there will be less significant changes in the yaw rate for a shallow slope, and you can observe only minor changes when you provide a steering wheel input. And for a zero crossing, it's nothing but when your steering wheel is zero, the yaw rate that you yaw rate for that point needs to be nearer to zero. This represents that the vehicle is going straight. And once we know these characteristics, like this is the behavior of the yaw and roll characteristics, and these are the general consideration that needs to be known. And after this, before going to this manual commands, we'll first go through the IPG car maker, and let's know about what is the general load case that we need to consider for this on-center test. So in IPG car maker, when you go, so in the IPG car maker main GUI, when you go over there, so in the file, you need to go to project folder and set it to your project team ID, team ID underscore team name, and you need to open in which product example. In the product examples, you need to go for vehicle dynamics folder, and then vehicle dynamics folder, you can go to handling folder. Under this handling folder, you will see numerous product examples that are available. In that, for the our load case for on-center test, you need to select for dyno steering pretest. Once you select this, so you can see the car and the tire model is imported, and also the manual commands are imported. Once you do that, you need to select the car and the tire model with respect to your model, and then in the manual settings, when you see uh, manual settings, when you see these manual settings needs to be updated with the manual commands that I will be further explaining. And in the in the scenario editor, if in case you go for the road file, here, due to you open the product example, the scenario road is generated, and you need to just verify with respect to this load, and you need to go to the segment, and once you go to this segment, you can, at the right side, you could see the parameters and the object list. Go to the parameters, you could see that length of the road is set to 15,000 meter. And just you need to pre-check the coefficient friction value that is mentioned is set to 0.7 or no. So to do that, so here you can see a green upward arrow. You just need to click over that. Once you click over that, you will enter into this region, and you need to click once more to that upward arrow. So you could see the configuration with respect to this road. So under this section, as I said, like you need to check that coefficient friction is set to 0.7. If it is not, you need to set it to 0.7 and save the changes. Once you save the changes, you could just go to the manual commands, and you could just update these manual commands that I will be explaining further. Yeah. So now we'll get to know about the load cases that we need to use for the respective load case. So at the first step, you need to have the manual settings start velocity to set to 0, and the duration of the time needs to be included as 15 seconds, and an end condition needs to be uh, pointed out, which is car dot v greater than or equal to 50 by 3.6. So once you set this, so this 50 by 3.6 represents that kmph is converted to meter per second, and Once you do that, you set your longitudinal dynamics motion to IPG driver as well as lateral dynamics motion to IPG driver. And later in the second manual, you will have the manual command with respect to steady state condition for duration of 10 seconds, and the longitudinal as well as the lateral dynamics motion set to IPG driver. And once you do that, the third manual step needs to be considered, which is an important uh, and the critical part of this manual commands that we'll be looking onto. Here, the manual commands is such that the steering wheel input is provided to achieve 0.2g lateral acceleration. So the time duration that we will consider here is 30 seconds, and we'll give a command which is eval first car.ay greater than or equal to 1.9 and steering angle is equal to steer dot wheel angle into 57.298. What does it actually means is, so we are evaluating the acceleration of 0.2g. So what my steering wheel angle for the vehicle is. So you need to consider the 0.2g lateral acceleration with respect to that what the steering wheel angle is. So to do that, this eval first car.ay greater than or equal to 1.9 is considered, and the steer angle is equal to steer dot wheel angle into 57.298 is the steer angle is a variable in which this steer dot wheel angle is saved, and this 57.298 is multiplied in order to convert the radians into the degree value. So steer angle is the variable that you will be looking onto for the car.ay greater than or equal to 1.9. And in the longitudinal dynamics, you will set the motion to IPG driver, and in the lateral dynamics, you will set the motion to sine and the mode to frequency, as well as frequency of 0.2 hertz needs to be considered. And for the first, for to calculate the lateral acceleration of 0.2g, so first we'll have a trial run wherein which we'll evaluate the lateral acceleration of 0.2g for, and we evaluate for that particular lateral acceleration what our steering angle is. So here is an amplitude value, just an arbitrary value that has been updated for you can consider 10 degree or 12 degree depending upon the case, and you need to use it as a reference value in order to evaluate the steer angle for 1.9 lateral acceleration. And once you set this manual command, later another manual command needs to be considered wherein which you will set it to idle, and you will set the time duration to 5 seconds, and the longitudinal dynamics motion will be set to motion, as well as the lateral dynamics it will be motion to sine and mode to frequency, and you will give the amplitude to 0. So these are the 4 manual commands that you need to consider for the load case, and the consideration of these needs to be made for the on-center test load case. So once you do that, let's go to the IPG car maker and see the changes that we have made. So I have the file that I already made for the respective model, and let me just open it. Yeah, so here's a model wherein which I have updated the manual commands, and wherein which you can see the lateral manual commands I just explained are updated over here. Once you do this, so what needs to be done next? So as I said, you need to evaluate your steering angle first with respect to 0.2g lateral acceleration, and that needs to be considered for further evaluation. So in order to do that, you need to you can first go, and here I have just considered a value of 10.12. So this is just an arbitrary value that I used in order to evaluate. So Now, if in case, in order to evaluate the point steering angle, we can just have this run. Uh, the file needs to be run for first, and once you do that, uh, you can go to the application and select the DVA, direct variable access quantity, in which you need to select for the steering angle that was previously told. And once you do that, you could just see that for the 0.2g lateral acceleration, this is the steering angle that is achieved, and this needs to be considered for further evaluation. So 10.091 is the value that you needs to input over here for the further evaluation. So this is the basic general manner commands that that needs to be considered. And once you do that, uh, let's just see the track that can be visible. So to just look on the track that we'll be having. So if in case I just go for a bird's eye view, so as I said, this is the track that we'll be having. So this type of track you will be seeing, and inside that the vehicle is inputted. And once you do this, since we are using sine over here, so let's get more understanding about what are the lateral dynamics motion commands are available. So you can, as you can see here, different motion views are available. So for the respective motion, why we have selected sine, let's get to know about. So the different lateral dynamics commands can be seen over in this reference manual. Once you go to the reference manual in driver manuals, you can just go to the lateral dynamics. Yeah. So as you can see over here, you can understand about the different lateral dynamics that are available for the IPG car maker. So here are IPG driver, sign steering, steer step, simple steer control, default control, lane change, and lane offset are the options available. So we'll be looking through the sign steering and steer step. So for steer step, you can see the graphical representation that has been given over here. So here is the graph wherein which you can see the linear and the smooth transition that is applicable. So for the steer step, the considerations are with the consideration is just that it is applicable for linear quantities. So it measures the response to discrete increments of step steer inputs that are provided. And in sine steering, if you could see that the graph representation there in sine steering we have sine and sine sweep. So what does this mean? So if you could just look over in the graphs, so you could see at the uh, initial point of this sine curve, wherein which uh, more sorry uh, uh, more discrete intervals that you can use. Like there is a sharp spike, and if you could see over in this smooth transition, you could see there is a continuity in the graph. So that's the difference that we have. For sine sweep, we'll be having this behavior, and for the sine, we'll be having this behavior. So in order to have the continuous intervals, so we use a sine as a motion in this low test case. And also the lateral acceleration value of 0.2g is being considered. So it is because the low lateral acceleration exhibits significant non-linearity over in that region. So in order to counter those, so this sinusoidal nature is considered. So as we have understood about the this sign and the steer step difference, and you could also understand the different options that are available from this reference manual. Now let's go to the plots that we needs to be considered for the load case. As I explained earlier, there are 5 different set of plots that you need to consider: the yaw rate versus steering wheel angle, roll versus steering wheel angle, and the steering wheel versus steering wheel torque, and the steering wheel torque versus lateral acceleration, and the lateral acceleration versus time. So we will just open the IPG control in the main GUI. Yeah, so as you can see in this IPG control, I have already set the y and x axis to the lateral acceleration versus time in the above block, and in the below diagram, I have set the y axis to roll, and in the x axis to steering wheel angle. So to understand that the steering wheel angle that we had provided, the to achieve 0.2g lateral acceleration, in order to check that, you can just simulate this lateral acceleration versus time. And in this graph, if in case you select shift left mouse button and then drag it, so you will select the range, and in this, so the maximum lateral acceleration that we are countering is 2.02 meter per second square, which is almost near to the value of lateral acceleration of 0.2g. So this is how you can verify once, and once you do that, so as you can see the behavior of the graph with respect to lateral acceleration versus time. So as you could see, so there is some non-linearity or the graph, as well as when the steering wheel input is provided. So you could see there is disturbances that is being countering over in this region. So also in case of roll versus steering wheel angle, if we just split it totally, you could see the plot that is um, being plotted over here. It's also having the disturbances, and as I showed earlier and discussed with respect to the yaw and roll characteristics for an idle vehicle that needs to be have. So it it is not resembling totally towards it, and it is not giving the linear behavior with respect to the plot that I have plotted. So these are the graphs that needs to be optimized, and the disturbances that are available in the vehicle model that needs to be eliminated. So how we could do that? Let us understand through the parameters that will affect those. So the factors that are affecting those plot nature are the mass of the vehicle, the weight distribution, the CG, and the suspension, as well as the spring rate of spring and suspension travel, as well as the tire and wheels, and also the moment of inertia values that we uh, are the factors that are responsible for the output graphs that we were looking in the IPG. So we need to optimize those values, and with respect to these factors, And once you do that, let me show you the more optimized vehicle. So we could just look onto how the response will be. If I could just open the optimized vehicle. Yeah, let me run it. Yeah, so as you could see, with respect to the parameters that I was explaining, so once you optimize with respect to those parameters, uh, you will have a more clear linear range of graph that we are looking onto. So yeah, as you could see the role characteristics at the below graph. So it is resembling to the graph that we were showing earlier, that we were discussing earlier. So this is how the factors affecting needs to be considered and needs to be optimized. And one more thing that needs to be considered over here is the post processing of this role and yaw, how to post process the data. So the graph needs to be selected, and you could just export the file to XLS file, your Microsoft Excel, and you can select the folder and you can just save it. Once you save the model, so you will be having this kind of data you will encounter in the Excel file. So once you do that, select, since the column needs to be separated by comma, so it is in one column itself. So let me show you how to categorize this. And once you select this region, go to the insert op go to the data option and click to the text to columns option, and in that section if you could choose the characters such as commas or tabs needs to be separated. So as you could see in the column, the characters are differentiated by comma, so you could just hit next and you could visualize over here that uh, the column is, the parameters are separated. And once you do that, click on finish so that you will get this two separate columns with respect to y and x axis. And this is how you will get it, and you need to select this values, and after selecting this uh, all values, you need to go to insert and you can go for chart section and plot it in scatter. So once you do that, this kind of depiction that you will see. Uh, so in this graph, uh, as you could see, it's similar to the IPG control that we were looking into. And in this, you need to select the graph, and to estimate the slope of the graph, you can just right click and go to add trend line. And in the add trend line option, you need to check on this display equation on chart so that the slope with this dotted representation will come, and the slope value will be in terms of y is equal to mx plus c equation. So this y is equal to mx plus c equation, uh, in this equation the m value that we are looking on is the slope of the graph that we are looking into. So this value needs to be considered when you are evaluating. And once you evaluate this slope of the graph, so since this is in y is equal to mx plus c, but if in case you click the add trend line equation, you will encounter a number equation. For representation purpose, I have made it as y is equal to mx plus c. As we gone through the graphs and how to post process this data. Now let's check on the output results that we'll be discussing further. So with respect to the output plots, how it was before and after optimization, you could see the change in the graph. So initially there were some abrupt disturbances at the initial stages and also when the steering wheel was angle was provided. But in the right side of the image, you could see the more linear behavior of the graphs. And this is with respect to the lateral acceleration versus time. And similarly for the yaw rate versus steering wheel angle. So you could see the graph previously and after optimization, the steering wheel angle, which looks more idealistic in nature. And to the point that like with respect to the graph that I was explaining, y is equal to mx plus c, the slope value that you considered. So that value plus c, the m value will be in the unit degrees per the steering wheel angle you calculated for 0.2 g lateral acceleration, which is the steering wheel angle. Yeah, 1 minute. So steering wheel angle for this amplitude steering wheel angle. So the m value that we have evaluated will be there, but we need to have the value in terms of degrees per 100 degree steering wheel angle for a roll. So for roll gain, you need to convert that value in terms of the respective steering wheel angle that you had have to degrees per 100 degree steering wheel angle. So how to do this is the value that you are getting, which is m. So you need to the value that you are getting. You need to multiply that m value into 100 divided by the steering wheel angle that you calculated for 0.2 g lateral acceleration. So by doing that, you will be evaluating the slope value with respect to the condition that is provided, which is degrees per 100 degree steering wheel angle. And this needs to be considered in the presentation. And as I was explaining with respect to yaw rate versus steering wheel angle, so similarly, the slope value that you take from the Excel data, you could just multiply that m value with 100 divided by the steering wheel angle that you have calculated for 0.2 g lateral acceleration. Once you do that, so once you do this, you will be getting the value for yaw gain as well as the roll gain, and the value needs to be considered for ideal purpose is in the range of 15 to 25 with respect to the units like degrees per second per 100 degree steering wheel angle with respect to yaw rate, and for the roll gain degrees per 100 degree steering wheel angle. So for both the things, the range of values that needs to be considered over here is 15 to 25. And let us take the other plots, which is the steering wheel angle versus steering wheel torque. So as you could see, the more scribbling kind of nature was there at the earlier stage in the left image, if you could see, and in the right image the steering angle versus steering wheel torque. So this kind of graph was encountered from the after optimization. And also you could see the steering wheel torque versus lateral acceleration. You can see the changes that has been made and how you could see at the right image the optimized graphs. Uh, that's it from my side. Yeah, thank you.
Yeah, thanks, Sampreet. Thank you for the session. So we'll now get to the last load case. Joe, are you there?
Yeah. Let me just share my screen.
Yeah, sure.
Yeah, my screen is visible, right?
Yes, yes.
Yeah. So hello everyone, I'm Joe. So I'll be continuing with the step test, the last of the five tests from this new format. So the agenda will be first I'll introduce the steps here to you. Then the ISO standards from which we are taking the rules for this particular test and the load case definition in car maker. Then I'll try to cover some theoretical understanding based on this test, and I will discuss about the expected outputs and the results that we have gotten and how to optimize your results. So let me begin with the introduction to steer step. So the steer step is a fundamental process in vehicle dynamics testing used to evaluate how the vehicle responds to sudden and sharp steering input. So the steering input can be given in two ways: either a rotational degree, in which it's the steering wheel is rotated, or a steering torque, up to which the until the steering torque is attained, the steering wheel is rotated. Either two kind of input that we can give. So this test is done to assess the stability and control of a vehicle in emergency maneuvers. So in the case of BAJA, you can consider if you're driving in a long time endurance race at full speed, any emergency maneuvers you have to take sudden right turns or a fast right hand corner or a sharp turn you have. When you are taking the turns, the stability and the control of your vehicle at that point of time, that particular time is evaluated through this test. So the purpose is to evaluate how quickly the vehicle changes the direction, the yaw response, how much the vehicle body rolls to the steering input, the roll response, and how the tire and suspension systems reacts in general. These two graphs would be like some of the outputs that you expect at the end of the PPT that we are going to get. And the test is actually based on ISO standard 7401 2011. So this is a standard for transient lateral response of road vehicles. This focuses on open loop testing methods. If you want to learn more about this ISO standard, particular for this test, and you can read more about ISO 7401. So particularly then on this scenario, how is steers the conductor? The vehicle is driven at a constant speed, typically a flat straight track. And when the vehicle is stably moving at a constant speed, a sudden sharp steering input is applied, at which point 4G lateral acceleration is induced in the vehicle. Then, after the steer step input, there is a very short duration of time. We are inputting a very fast steer step. Then we are holding the steer step for some time to know how the value stabilizes. So this is the general scenario. So the track layout would just be a large rectangular field, and the speed would be 40 kilometers per hour that you have to maintain, and there should be no braking in between any of the maneuvers. And the lateral acceleration that has to be attained with the steer step would be 0.4 g. So I'll just now open the CarMaker GUI and I will explain to that. So let me first explain how to take the track. So this track is similar to the one the used for the on-center test. You can follow the same procedure. Else, if you want to import a new track, you can also just import a road file from the product examples under example synthetic and test track. If you can see this driving dynamics area, any of these driving dynamics area would do good. This is essentially just a rectangular empty field for us to test our maneuvers. That's it. So choose either one of them, and we are good to go for the maneuvers. Uh, the first maneuver would be accelerating your car to 40 kilometers per hour. So initially, the starting position, we are giving longitudinal dynamics IPG driver with a cruising speed control of 40 kilometers per hour. So now for 20 seconds, we have given this maneuver. So, but when the IPG car maker finds that it has reached 40 kilometers, then this maneuver will end even if it's before 20 seconds because of the end condition that we have given. That is car velocity greater than or equal to 40, this maneuver will end. So this is the first maneuver. Then after 40 kilometers per hour is reached, we are now trying to find the steer angle in which 0.4 g acceleration is induced in this vehicle. So this is similar to what Samprit also did for 0.2 g lateral acceleration. Now I am doing it for 0.4 g lateral acceleration. This is the exact same maneuver. We're evaluating first when car dot AY greater than or equal to 3.92. So lateral acceleration 3.92 meter per second square, that is essentially 0.4 g. If that condition happens, then the steering angle in which that condition happens is stored in a variable named steer angle. So, and there is also an end condition such that when it is 3.92 lateral acceleration is reached, this maneuver will end. So, in here, the longitudinal dynamics is still maintained at 40 km per hour constant. And here in lateral dynamics motion, we are using steer step. In the steer step, we are just putting from start to duration, 360 duration, and I'm giving an amplitude of 360 degree. This essentially means it is slowly increasing. So if it's 360 degree, then it means for every 1 second, the steering input is increased by 1 second. So we are slowly increasing the steering wheel to find where in which steering angle the 0.4 g would be induced. And then after this, then comes the steady state condition. So now we have found out the steering wheel angle and have stored it in a variable called steer angle. Now for the steady state condition, we are trying to make the vehicle move in a straight lane for 10 or 20 seconds so that the vehicle would stabilize and the variations from the last turning maneuver step would be gone. So this is just again a steer step. Just there is no need for steer step or IPG driver anything. Just put as no lateral motion at all. And longitudinal dynamics IPG driver again cruising speed of 40 km per hour. We are maintaining that. And now we have found out the steer angle. Now we are in steady state. And now we are going to go for the actual steer step maneuver. So in the steer step maneuver, we are putting a steer step input. The lateral dynamics will be steer, and as usual, longitudinal dynamics is still maintained at 40 km per hour. In lateral dynamics, steer step maneuver, we are just the amplitude is just 1 second. For 1 second, we are giving an amplitude of 360 degrees. So what this step means is within 1 second, the steering will be rotated by 360 degree. But actually, it won't be 360 degree because now the steering wheel angle is greater than or equal to steer angle. This particular end condition will make sure that the steer wheel angle is equal to the steer angle stored from the finding from the step 2. It will end. So the maneuver will end. So 40 degree 0.4 g is occurring, and we have saved 40 degree as steer angle. When 40 degree is achieved, this maneuver will end. So another thing to note is that in the longitude IPG driver parameters, under use additional parameters, you have to make sure your maximum steering wheel angle is 360 degree per second. It should not be more than this or not too less than this. So this at least this should be maintained, and so that we have an accurate representation of how an actual driver will rotate the steering wheel lever. If you're going to put 500 degrees per second, it is not actually possible for an actual driver to rotate that fast in a vehicle in an emergency situation. So you have to make sure it does not exist 360 degrees per second. So now the steer step is executed. Then holding the steering angle. So for 10 seconds, for longitudinal dynamics of 40 km per hour, we are again maintaining that speed. And the motion is steer step again. And for the duration of 10 seconds, the same as the duration, we are putting the amplitude to 0. But what I said, we have to hold the steering wheel in that position as for the last steer step. We should not make the steering wheel go straight. That is why we are pressing this. The value is offset button. What this essentially does is that the last maneuver, so in the steer step, there is a particular degree in which the maneuver would have ended. So that particular degree, if it's a 40 degree is the steer angle that the steer step ended, the 40 degree is now calculated as 0 degree for this maneuver. So the 40 degree is a new 0. So the steering wheel is held at 40 degree for 10 seconds. So this is the maneuver steps. Now I'll try to run a vehicle and show it to you how it shows in the IPG movie window. So you can see now it's accelerating to 40 km. 40 km per hour, it's accelerated. And now the steering wheel angle is increased slowly. As you can see, the steering wheel is moving slowly towards the left side till 0.4 G is induced in this vehicle. Still it's going on since 0.4 G is not yet induced. Now 0.4 G is induced. We found out the steering wheel angle at which 0.4 G was induced. Now it's again went for steady state and then the stair step and holding stair step. The sequence is done. So you can get a visualization out of it. Okay. So as you can now, I use the IPG control window to show you the results that I've plotted along IPG movie. So this is how you get a basic results. Now I'll talk a little bit more about how to interpret this results. Then I'll come back to explain what the specific results are actually. So in this particular test, we are more focused on roll and yaw rate. So what is roll? Roll is the, as you can see in the diagram, roll is the rotation of the body along the axis that is passing parallel to the travel of the vehicle. So along the axis, when the vehicle rolls, that rolling factor, that is one of the important factors they are considering in this test. As you can see in this diagram too, you can see the vehicle is rolling to the right side when taking a left-hand corner. This is roll. And Yaret, as explained previously by the people who conducted this before me. So the speed at which the vehicle rotates around its vertical axis. So you can consider this blue color line there, the z-axis. Upon the z-axis, how fast the vehicle is turning. So that is the yaw rate. Roll and yaw rate are our most priority considerations for this particular. So how they affect the vehicle dynamics. So just to give you a bit of an understanding on how roll and yaw rate are actually important. Like roll and yaw rate actually influences the stability. Excessive roll change could lead to lack of tire grip. So if you lose tire grip, then essentially use traction. And yaw rate, when there is too much yaw rate, it could lead to oversteer. We could design for vehicle could be designed for oversteer, but still, if the vehicle is uncontrollable, then it is no point. So everything must be in balance. So this roll and yaw rate affect the stability in handling in their own way in such. And for load transfer too, the roll determines how much weight is being shifted, or the weight transfer is also one of the reasons for roll, you can say. So if you're reducing roll, the weight transfer to the outer wheel could also be controlled. Another is cornering efficiency. When there are too much roll and yaw, the efficiency in which you are taking the corner would decrease actually. Another thing is tire wear, obviously, because if you are having a lot of roll, then the contact patch of the tire is not uniform. Then there is more degradation of the tires in the outer region or the inner region based on your misalignment during roll. So how to interpret this test result? So you need to produce some plots. After this test, you have to run all these plots and you have to showcase this plot to the presentation. The plots will be steering wheel angle versus time. How you have inputted the steering wheel angle, how much steering wheel angle induced 0.4 G in for you, and that kind of information you could interpret from the steering wheel angle and the lateral acceleration from time. This plot tracks how lateral acceleration is increasing with your steering response. So, like when comparing the steering wheel angle lateral acceleration, we could have an understanding of which point we had a 0.4 G and how 0.4 G is maintained continuously throughout, and ensuring that you have done the steer step test actually correctly. And moving on to roll angle, visualize how much roll it happened to the vehicle during the particular steer step and how it stabilized. That kind of visualization will get from roll angle versus time. And steering wheel torque is the steering wheel torque required by the driver to hold and to input the steer step. And yaw rate versus time is the plot which reveals how quickly the vehicle responded to the steering input. Now, those are the graphs that you have to display, and the output parameters, the exact values you also have to show, or the roll overshoot, yaw overshoot, roll steady, and yaw steady state values. So what essentially are these? As you can see from this first graph, the steering wheel input, the steering wheel angle is suddenly turned to 20 degrees, particularly very shortly in a stair step. And as you can see in the lateral acceleration, for 200 kilometer per hour, that line, if you can see, you have a very high peak value. Then it actually undulated and it became less than the peak value and it stabilized at a lower end. So this peak value, that one you get immediately after the stage step input, is called the overshoot value. And the value that you get after stabilization is called the steady state. Similarly, it is more visible in the case of yaw velocity. As you can see, the overshoot value. This is the overshoot percentage, how much it has overshot, that you can say. So this is the overshoot peak value and this is the steady state peak value. So these are the parameters. These are the four values that you have to showcase along with those five graphs as a minimum. These are all bare minimums. If you can interpret more results, you are always welcome to add much more results if you can. So now I will show you the possible outputs. So let us see. Before the possible outputs, I will again run another test case and how it's different. As you can see in the first test case I run, that as you can see, there is so many undulations in the lateral axis. This essentially means that your suspension parameterization it's not correct. Your damping is not going on. There is a vibration. You are either under damping or over damping, and your KNC parameters need to be looked at again. So that is the inference from this. And also these graphs also there are several mistakes that I will point out later, but this is not an optimized one per se. So we'll now run again another car which is optimized. We just focus on the graphs. As you can see, these graphs are pretty clear, and you can definitely see the clear overshoot here, overshoot and steady state. These are the roll and yaw rate I was talking about. So these blue line is the yaw rate, and the red is the roll rate. You can clearly see how they have overshot and how they have stabilized. This is a more proper optimized vehicle. And now I'll showcase each of the graphs in detail and how they are optimized and such. So these are the possible output. These are the possible outputs, as you can see, initially for the driver steering angle. As you can see, it is stabilized in a particular value, and around this particular time period, we have inputted the steer step, and then the steer angle is held at the same position for around 10 seconds. And this is the car velocity graph. As you can see, it is maintained at 40 kilometers per hour, and there is a very slight drop in the velocity when you actually input the steer because of the lateral maneuver that you are committing to. There is a very, very slight drop in the linear velocity. And as you can see, there are only 40 and 39.8. There is only 0.2 kilometer per hour difference. And you need to make sure the difference is not that much. Because this kind of very small range of variations is accepted, but still it should not be very large. And for the steer torque, like this is some of the improbable outputs that you can possibly get. So as you can see, the steer torque is at the constant level, and when the steer step is actuated, when you are turning the steering wheel very fastly in 1 second, your torque is actually getting a negative value, which is highly improbable. This essentially means that in the KNC and in the mass parameterization for the steering wheel angle was calculated, you have mistakenly inputted something right in the moment of inertia and the mass parameters for the related to the steering inputs. So those you have to have an again look at. That's the same case for this one too. So if you have sudden 100 Newton meter steer torque speed, and then you are again stabilizing at 2 Newton meter per torque speed. This is very highly unrealistic when you can get so high of a steer torque suddenly and get back to a 2 or 3 Newton meter torque then in a steady state. So this is the most realistic graph. Like we are going in a constant bed because of the sudden steer step, you have peak value of 5 Newton meter around there. 5 Newton meter, you have got the peak value. Then you get stabilized again around some between 2 and 3, you are stabilized with the steer torque, and you are having the same steer torque for the rest of the time till the maneuver ends. And these are some of the other improbable outputs. As you can see in the first vehicle, this was the lateral acceleration that I have got. Lateral acceleration was very highly unstable. And in this particular graph, you can see the lateral acceleration is continuously decreasing after the CSM. I am trying to maintain it at 40 km per hour, but the this lateral acceleration is continuously decreasing. This indicates there is some issue with your powertrain modeling, and this is a possible output. This possible output is like when you are actually trying with the peak value, it may slightly overshoot from the 0.4 G that we actually want, but then again it stabilizes at 0.4 G. This is the most appropriate output that you can get. And these are the improbable outputs for the roll and yaw respectively. And the yaw rate, as you can see, there is a overshoot value. Then it stabilizes again when you're holding the steering wheel angle in the same position. The difference between this for this particular vehicle is around 12%. The overshoot value you have to take either from the control you can take directly, or you can export the values to an Excel sheet, and from that you can get the maximum value and the stabilized value, and then you just do the simple formula of overshoot minus steady state value divided by steady state value 100%. It will give you how much is the overshoot higher than the steady state. So these percentages, 12% is the value we got for this particular vehicle. Generally, for BAJA vehicle, it should not be more or less, it should be less than 20% of the steady state value. If it's more than that, you are more likely to be an unstable vehicle. And similarly, as you can see in the yaw rate, there is almost no undulations at all. It is very smooth. This essentially means you are very, very over damping your, overly damping the during on. This kind of damping will actually make your vehicle more stiffer and less reactive. We are focusing on more stability in this case, but you will lose out on maneuverability if it's so damp and it's so constant in this when in banking. You are losing out on maneuverability to gain on stability. And this particular yaw rate, again, it's continuously decreasing with time after the steer step. It should not. It should attain a peak value, then it should stabilize. That is how a normal vehicle behaves. If it's behaving like this, then you have to check your parameterization again. Make sure you have modeled correctly your vehicle. This is the same case for the roll angle 2. Roll angle, as you can see, for this particular vehicle, there is a 3% overshoot value. This is a very less overshoot value. This essentially means this vehicle is focusing on more on the stability side. The same as for the yaw rate definition. And by using the same formula, you can find out the overshoot percentage, and you can showcase these overshoot percentages as well as the overshoot values and steady state values for the roll and yaw to the judges, along with all the 5 graphs. So to give you an idea of how to optimize the vehicle to control this roll and yaw as per your design for either oversteer or understeer. So one of the easiest things you can do is adjust the stiffness and dampening. The roll stiffness and roll dampening are affected by a lot of things. The spring rate and the dampers capabilities are one of the things by which you can affect the roll stiffness and roll damping. By controlling this and by controlling the variations in the roll stiffness and roll dampening between front and rear, you can control the yaw rate. If it's different from front and rear, that is going to be different. That this difference could be utilized to control the yaw, how much fast it is reacting to the inputs. And suspension kinematics, obviously, by improving your suspension kinematics, by placing your roll center height, you can control your suspension kinematics, and thereby controlling the roll and yaw responses. Particularly roll center height, the difference in roll center height. If you connect the roll center height of front and rear, you will get a roll axis. This angle of roll axis actually plays a role in controlling your yaw and your roll actually. So you can actually control the roll axis, the inclination of the roll axis along with the vehicle. These are some of the parameters that you can look into and control, so such that you can optimize your vehicle for optimum maneuverability or stability, whichever you're focusing on. And similarly for weight distribution, a more front or rear heavy vehicle would behave differently to another thing. So more rear heavy vehicle would probably then have a tendency to oversteer. So such things you can control in your basic design to achieve what you want, and actually controlling your center of gravity by optimum placement of your most heaviest object like gearbox, engine. You can have a slight control over this again. And in the most basic sense, the wheelbase and track width also gives you the more narrower the wheelbase, more the track width, the more dynamic it would be, the more the rolling yard change would be, and more wider and more longer these are, the effect will be reduced. So, so these are the ways in which you can optimize your vehicle. Now, I'll again just have a little look at this control graphs to uh, show you how this actually happens. Just give you one summary. So essentially, we are accelerating to 40 kilometers per hour. Then we are slowly increasing the steering wheel angle until we find out the angle at which 4.4 G is attained. Then the steady state condition, we are letting the vehicle move in a straight line in a steady state. Then we are giving a steer input for 1 second, in which the vehicle steers to the already predetermined angle. Then we are holding the steering angle for 10 seconds. I'll just again run this in the movie and you can have a visualization of how it's working. So you can see the vehicle is moving in a straight line for stability. Then we are finding out the steering wheel angle, which the point 4G is occurring. Then again steady state. Now the steering input will be applied. Then we are holding. So this is essentially the end of the maneuver. So maneuvers are very simple. So that is and these are the graphs we are getting. The car.ay would be lateral acceleration, car.b would be the velocity of the vehicle, the vehicle roll would be the roll angle, yard rate would be the, as you can see, the rate at which the yard changes, and the steering wheel angle. From this, you can see clearly how the vehicle has overshot, then it is continuously maintained at the same level after it got overshot. So now you can change it by either by dampening, you can control the dampening, or you can play with the kinematics behavior to reduce it or increase it. As long as it is within the limits, it's not issue. You can either go for stability design in which the vehicle values are so less, or you want your vehicle to be more maneuverable. In that case, you will have a little bit more roll and yaw. But you have to maintain that, make sure that it is within less than 20%. The overshoot value should be less than 20%. Okay. So with that, I have covered the optimization. So that is it from my side. Thank you all.
Yeah, thank you, Joe. Thank you for a very detailed session. So I hope teams you have got a gist of the 5 vehicle dynamic scenarios that you would have to do a presentation on for your static event. So all the graphs, all the outputs that we have talked about for all the 5 scenarios is something that is at least expected. So you are also open to including some other parameters that you have found out from your own research that you think is also affecting the dynamics, and it's also a key parameter in optimizing the vehicle. So you can also include that, and also, as I mentioned before, you can include any other extra scenario that you have considered other than these 5 dynamic scenarios in your presentation and talk about it. So yeah, that was all for the 5 dynamic scenarios. So now we'll just quickly go on to the last session, which is the MATLAB battery modeling in MATLAB and the co-simulation with IPG CarMaker. So Sampreet, are you there?
Yeah, I'm just sharing my screen.
Yeah, thanks.
Is my screen visible?
Yes. Yeah.
Thanks. Yeah. So, hello once again to all. So, in this session, we'll be talking about the battery modeling using a MATLAB and also the range evaluation with respect to using IPG car maker. So, what's there in the agenda for this session is first we'll the overview of the battery systems and get to know about the battery. Later, we will understand the meaning of SOC and then we'll go through the interface of MATLAB software, focusing on Simulink and Simscape interface. And once we know about the software, and we'll understand about the charging and discharging circuit using the MATLAB. And after that, we will go through about how to model a battery pack using MATLAB, and we'll understand the modeling of a battery pack using an app. Once we go through these all context, later I will be explaining the steps to interface the IPG car maker with MATLAB for course simulation. And at the last, we will see how to evaluate range using IPG car maker. So let's get started. The first, in the overview of battery systems, to build a battery model using MATLAB, what is most important is to have a basic understanding of the blocks that are available in the Simulink for setting parameters and know how the interaction happens between the Simulink and the Simscape um, in the MATLAB software. To just familiarize you with the batteries, consider an example such as battery which is acting as a power source for smartphone or the laptop or even an electric vehicle. So all of these require battery systems in order to ensure that it is having a safe and optimal operation. So what does this battery pack includes is the influence of the temperature from the environment as well as the charge level indicator and the charging algorithm that is used in order to charge the battery pack in the battery pack systems. So let's just have an introduction with respect to a battery. So let's understand how these batteries that are modeled can handle wide ranges of scenario. Like an example to give you handling with different weather conditions, the battery will be accounted to different battery conditions, how it affects. Uh, this can be achieved or done by knowing the unit cell behavior of the battery. So with respect to the cell level, so you can understand and know about the consideration of the different weather conditions. So the cell generates, so the what is cell actually? So the cell is an um, source where from which you will develop the model, and the cell generates the electrical power through electrochemical reaction. The performance of it will depend on the several factors that may be remaining charge in the cell or the temperature of the cell and the age of the cell. So the equivalent circuit model that you can see over in this image represent the battery cell behavior as a function of these factors that are presented in this. So by changing these factors, you can configure new battery cell and accordingly it can be configured. Later, let's understand what does SOC means. So SOC stands for state of charge and it is an important parameter. And in battery systems, the one of the important variable that will be available is the charge level. And this charge level in battery systems helps to prevent the overcharging and over discharging conditions. And therefore, the SOC is an influential parameter in terms of battery systems. And it is defined as the ratio of the current charge to the cell's rated capacity. So before going through this with this MATLAB model, let's first understand the interface of the MATLAB software and see how the Simulink and the Simscape blocks are included. just for the purpose of that, I will just open the MATLAB software. So this is the MATLAB interface that you will be having, and inside that, inside the home, you will be having different tool kinds over here. And inside this, you can go for Simulink. Once you tap on the Simulink, it will be initialized and you will get a new window wherein which it will be uh, giving you the consideration of the blank model and different library that you have installed. So you can just click on the create model for a blank model. Once you do that, it will initialize the new window and a new Simulink window will be created. So what's there in the library browser is the tools that are available and the blocks that are available in the Simulink. So we'll not be going in all the block sets. We'll just consider the Simulink and the Simscape. In the Simulink, you can have wide range of sources once again, and there are common use blocks uh, such as bus creator, constant values, mux values, and so on. And similarly, with respect to other categories that are involved here. So you could just explore at your end and what are the different blocks that are available. And also in Simscape, you could, when you click on it, you will have different utilities that are been in there, different blocks. So the foundation library, utilities, and battery, driveline, electrical, fluids, so on. And in that, if you could see in the foundational library, once again, you have different set of uh, departments like electrical, gas, hydraulic, and so on. So we could just, when we just go in electrical, so another three elements that we occur, which is elements, sensors, and sources. So here are the basic blocks in Simscape electrical model. So you could use it in for physical modeling of your battery. And these tool sets that you will be using for the in order to model the battery systems and all, and you can explore at your end that different libraries that are having in the Simscape. uh, but as of now, let's move on to the next thing that we were talking about is the battery charging and the discharging circuit. So let me just open the Simulink model that we are having. So this is a basic layout of a simple battery charging and discharging circuit. And this is how you can connect the Simulink blocks and the Simscape as I explained. And you can create a physical model. So what do we have in this battery circuit is we have built a battery with a single cell with having the resistor and the capacitor involved in it, like the in the previous, like as said, the factors that are responsible. So equivalent circuit model, how you can create. So like this, I have connected a basic cell model, battery model, and with respect to that, the current sensor and the voltage sensor are connected, and this model is considered in order to check the charge that is charging condition as well as the voltage supplied to the battery and the power requirement. So in order to simulate this, you need to have a solver configuration in consideration in order to run the physical model. So without this, you cannot run the physical model present over here. So after connecting these all parameters, let's just check what are the graph outputs that we are occurring. So this is just an basic model that we can account for in order to consider the charging and the discharging circuit. So if I could simulate it for this time, so in the scope block, when you open it, you will get the graph respectively. So this graph shows that like the charge level is decreasing, and similarly the power and the voltage values fluctuating with respect to the load condition that has been given. So in the load, there is a signal builder that has been used. So in order to get through with different load values, different load conditions, so how the battery is operating. So this is just an example purpose where in which like you can use signal builder in order to set these values and create your own signal conditioning. And with respect to that, you can have this graph that I had shown earlier. So this is for just basic understanding about how the charging and discharging of a battery system works. So over here we have given a gain of -1 divided by 3600. So since the minus indicates that it is starting to discharge, and it could multiply with a positive value, it will start for charging condition. So as we have battery charging and discharging circuit, so this is a basic model wherein which you use simple block sets of Simulink and connect it in this battery pack, and then connect it with the other circuits to evaluate the charge, voltage, and the power of the battery. So we do have more advanced options in Simscape. If you could go to Simscape battery, where in which in the cell category you could see there are two options that are available. One is battery and the battery table based. So if you could just open this battery, so you could see, let me drag it. So it's a battery pack wherein which it will be asking for the nominal voltage, the internal resistance, and the battery charge capacity. So instead of using RLC circuit like resistance, uh, capacitance connected in series, you could use directly this battery block, and you can set this value and you can configure this battery pack. So this battery in this battery, and if you could just open this battery table based, you could see the difference is the difference between these two are the battery only is a low fidelity model, and the battery table based is a high fidelity model. What do you mean by low fidelity and high fidelity model? So in this battery, so you could just have an understanding of for a quick estimate of parameters and for initial exploration of the design of the battery. And if you could just go to the battery table based is a high fidelity model wherein which it takes into account of different tabulated values, experimental values in consideration. So if you could see that in battery table based, there is a selected click to select option. If you could just select it, it will give you another page of set of battery packs that are already available um, in parameterization manager. So if you could see, you have different part numbers, manufacturer, and different battery types. And with respect to that, the capacity and the voltage of the battery, and all, as well as the weight. So if you could choose any one of them, and you could just simulate at your end in order to get understand about how this model will how this model has the different parameters uh, in consideration with this capacity, voltage, and weight, other parameters that are included. So if I just select apply all and just close this, in the battery it is select that I have shown earlier, and with respect to that, the different values with respect to SOC values, the temperature, different temperature conditions, and the circuit open circuit voltage as well as the terminal resistance of the battery and cell capacity is all been directly installed from that battery parameterization manager. So you could see this configuration is a high fidelity model because it takes into account of the experimental values that has been uh, carried out for that battery pack. You could use this model and check for the output and how these parameters are influential and to just understand with respect to the dynamics of this battery pack. So as we covered with respect to this battery charging and discharging circuit, so next let's move on to the battery pack modeling. So in battery pack modeling, so SimScape battery, as I showed earlier, it includes MATLAB objects and methods to automate the creation of SimScape battery models instead of using the more traditional of building the circuit using Simulink plots that are available. So these MATLAB objects allows us to define battery design specification, visualize the battery in 3D space environment, and customization of the model resolution during simulation, and also generate the Simulink library from there to that contains the custom generated blocks. So providing that using these MATLAB objects that I will be showing further. So that will account for generation of Simulink library that you can import and use as a SLX file, Simulink file. So what do these bring is these blocks will assist us with the virtual battery design and verification and also explore design parameters, functionalities, and understand the behavior of the system. We can build a battery pack by connecting a bunch of cells together. So we'll start building it from cell level. So as you could see in the graph, so this is how a 3D space environment that I talked about. You can look over. I will further show in more detail how it will be. And this cell configuration you will start with, and later it connecting in series or parallel combination for the required condition. And if you connect in series, in terms it increases the voltage requirement, and if you connect the cells in parallel, increases the energy capacity of the battery. So these several connections of battery cell in parallel and series, we call it as a module, battery module. So and these several battery modules constructs to a battery pack. So that generation of battery pack is over here. So this battery pack is created in order to increase the energy as well as the power of the system. Now, as we got to know about the battery pack modeling, uh, let's now go through the app that helps us to build it in much simpler way. So we have an app for battery to build a battery pack, wherein which you can configure the parameters and you can check for the design understanding of the battery pack. So as you could see, this is an interface of the battery builder app, wherein which there are two types. One is for battery builder and the battery charge. Battery builder will give an understanding of the layout for in which you will build a battery pack with respect to cell and the parallel assembly module and module assembly and the pack. And in the battery browser, you could uh, see the arrangements of cell and the different example that are available. And in the battery hierarchy, once you model with respect to cell, parallel assembly module, and module assembly, and then pack, so you would see the hierarchy that you will be doing, and you could just check on the parameters that you were able to provide. And at the selected battery section, So you will have a 3D space environment where you will be able to visualize the cell block, how it is arranged um, with respect to this 3D graphical nature. And in the right side, we have cell properties or the battery properties. So wherein which you will have to input the different parameters to configure the battery pack. So let's understand in brief. In order to understand in brief, you could just go to the browser and check for get started with battery builder app. And in battery builder app, you could see the mentioning of the things that are available and how to create the battery pack by using battery builder app. So to open the battery builder app, you need to have a version of R2023A or higher. The previous versions don't um, have this battery builder app. And in order to open the battery builder, you can give command in the command section and open it, or else you can go to the Simscape block, and you could go to the Simulink and go to the app section, wherein which you will in the Simscape section you can choose the battery app. So you could do it in two ways. And once you do that, as I explained the interface that is being there, so if you could go to the cell level and it will create for a new cell arrangement and the cell properties that you need to provide. As I said in the battery properties, it will be showcasing what are the parameters that you need to provide in order to do the arrangement. So we do have three geometries that are available in this battery builder app. One is cylindrical, pouch, and prismatic. And selecting those will yield to different arrangements. Different geometry arrangements will ask for different geometry parameters that needs to be updated. Once you do that, you need to create. You can also include the temperature dependence as well as the age capacity and also the thermal port in consideration. And once you do that, in cell model options, um, you could just create a layout. This is for a pouch geometry, and for a pouch geometry, this is how for a single cell the battery builder app looks like. And later, if you after building a cell, you need to create a parallel assembly according to the requirements. You can update the number of parallel cells that you want to build, and the gap between the cell blocks that you want to involve, that can be uh, imported over here, and you can see that it will automatically give you a configuration of three parallel assemblies as given over here. And similarly, with respect to module assembly and the pack needs to be considered. Once you do that, so here is how a battery pack looks like in this example. So here is a battery pack that you would build when you configure with this battery builder app. Once you do that, so you can import the thermal boundary conditions wherein which you can involve the ambient thermal path as well in order to see the understanding of how the thermal behavior acts on the battery. And also you can include the coolant thermal path if in case you want to, or you can select none. And with respect to that, you can go more through this context as get started with battery builder. You could read on this and you can start at your end to try this. And once you do that, after creating a battery pack, you can go to the battery build options, wherein which you can select for the directory and the name that you want to have. And after creating the library at the create section, you can export it to SLX file like this. So a Simulink block will be created in this manner. Once you do that, let's understand what are the blocks that we'll be having after that. So as you could see, after the battery pack is created and installed into the Simulink file, so you can have three types of ports that connects to the external circuit that you want to build. So this is the electrical ports that you will be having, the plus minus connection and the thermal port. Like we opted for thermal condition behavior in consideration, as well as the measurement ports. The cell level parameters that you want to measure, the SOC parameters, the voltage and the temperature effects for the cell level, you also can configure via these options. And inside this battery pack, you will have much more detailed layout that from battery builder app you can create. If in the section inside the battery pack that we will be having block, the pack system comprises three major sections. One is the battery module assemblies and the output signals, as well as the thermal boundary conditions if it is selected. So this is how you can build a battery pack using a battery builder app. So this is how the interface looks like for a battery builder app. And as I said, in order to get to know more about this battery pack configuration with respect to battery builder app, you can just Google it with get started with battery builder app to know more about it. And this is the battery pack simulation that I had created using the battery builder app, using the MATLAB software. So after configuring this battery pack, you can just layout it to with the circuit that you want to bring in and check for the behavior of the battery pack with respect to nature, the charging or discharging circuit, or the battery temperature that you want to check, as well as the SOC level of the battery pack and the voltage level of the battery pack. So you could see at the right side the image showing how typical behavior of the battery pack works, and with respect to different options that you want to build, like the SOC level or the initial and the outlet that you want to have, you can configure it, and different charging conditions. So here we have used constant current, constant voltage algorithm to charge the battery pack. So this is a layout that you can create using this interface. So we understood on how to do battery pack as of now. So now let's understand how we can co-simulate with co-simulate the IPG car maker with the MATLAB software. So in order to do that, you need to go to the initial page of the MATLAB when you open it. So inside that you need to select the battery folder to your directory team ID team ID underscore team name, and inside that, if in case you will be having different files, you need to select for src underscore cm4sl, and in this folder you will be having general files applicable over here. So in order to have the core simulation generation, so you need to select for this cmenv.m file. Just double tap on it, you will get a code, and if in case you run it, the directory of the path will be added from the this version of car maker to the MATLAB software. And once you do that, you can open the generic.mdl file. And if in case you open it, you could see the generic car model is open. And inside this, you can open the car maker GUI from here. And you need to allow the file, and you can open the GUI of car maker from over here. So this is how you can send this is how you can configure the co-simulation of IPG car maker and the MATLAB. This is the procedure that you need to follow in order to do that. And if you open the car maker option, you could see the block sets that have been created. If I just go in the vehicle control, you could see the more parts, how it is connected. So you can explore how these interrelations are connected. And from here you can start the co-simulation if you want to, like, the consideration of co-simulation can be done from this way. To just notify you, so if you could just go to the help in IPG GUI and go to the release notes. So inside the release notes, you could check for the MATLAB config MATLAB software that you can include. So the compatible software version that you need to consider in order to do the co-simulation. So inside the MATLAB section, you can see in the 16th page of user guide, these are the possible options that you can check, which is from release 2020A to release 2022B. So these are the options these are the software options um, that you can use in order to have the co-simulation uh, done with MATLAB. So now we understood about how to do the co-simulation from connection from IPG, MATLAB with IPG CarMaker. Now let's go to the last topic of this session with range evaluation using the IPG CarMaker. So yeah, let me close this file. So if we go to IPG CarMaker, and in the IPG CarMaker, first you need to select a product select your file with respect to car, and the tires needs to be imported. And inside the road, if you need to use a product example for you need to use a product example with respect to a circular track that you can have. You need to just have an import from your file, and you can go for product examples. Sorry. So you can open the product examples. Inside the product examples, you can go to the vehicle dynamics handling, and you could just select the steady state circular product example. Once you have selected the product example, if you need to update the car model and the tire model to your respective model, and This is how the track that will be available. So once you do that, uh, you need to have the manual settings that needs to be updated. And in order to do that, let me show you the file and the manual commands that can be provided. Let me open the test run file in order to show you. So as you can see, the model has been imported, and inside the manual settings, just you need to give a you need to give set the speed to top speed, which is 50 kmph in consideration for this. And inside the command section, you need to set the command as eval first pt.bcu.battery hv dot soc less than or equal to the value that you want to check, like for 20% soc you want to check. So according to that, you need to in order to estimate the range value, you can use this eaq as car.road.sroad, and I have saved this function in this car distance variable. And if you just run the simulation, you could observe you can observe in dva like the range value with respect to the battery percentage. So as of now, I'll just show you with respect to 98%, just doing that. So if I could just run the model and open the DVA. So inside the DVA, you need to, in the quantity section, you need to choose for, okay, I need to run the simulation. Yeah, so once you do that, you can go for DVA, DVA section, in which you can see a car distance variable over here, and you can choose it. Also, you can see the back pt dot pt dot PC. So to check the battery SOC value, so as you can see, it's still running, but the value for car distance at 98% is evaluated to 282.425 meter. So this is how you can evaluate for range for the range of the vehicle. Yeah, this this is the procedure that you need to consider for range evaluation, and yeah, that's it from my side. Thank you.
Yeah, hi. Thank you, Sampreet. Thank you for that detailed session on battery modeling and range evaluation. So, teams, you can, from the understanding and the theoretical aspects that Sampreet covered, so you can build your own battery models in MATLAB. You can explore that. You can also do co-simulation with it. But for the vehicle model submission for your VD simulation ROM, ensure that you don't submit your battery models. Because if there are any issues, then yeah, there will be problems at the later end. But for your presentation rounds, to include, if you're considering some kind of a scenario, you can implement and talk about your own battery model and how you optimize it, and or the whole vehicle range, also how much you are able to optimize. You can include that as well. So yeah, so now we are open to Q&A. So yeah, if you have any questions for us, you can just let us know.
So there's just one thing that I'll like to add. You guys can submit the battery, like if you have modeled the battery packs in MATLAB, you can submit those using which you can do co-simulation if you are planning to do so. But you need to ensure that the model is working properly, and the vehicle is able to cover the entire track. because it might happen that the SOC is dropping very quickly and it is not even able to complete the one lap of the track. So you need to even if you are going to submit, if even if you are trying to use MATLAB's battery pack and do co-simulation, you need to ensure that it works properly so that later on we can't help you if the simulation is not working properly or if you're not able to complete even a single track. So yeah.
Yeah, thanks, Satraj. So the recording, yes, we will let you know. You will receive a mail notification that the recording link as well. Yeah. So any other questions regarding the new format uh, or the content that we had presented? Anything with respect to that? So teams, you can give a thumbs up as well if you like the session, or if you have no questions or everything was clear, you can just let us know at least. Uh, we can't share any PPTs or PDF materials, but yes, you will get the training video as well. And I'm sure at your end also you would have recorded the session. So the battery question. No, it's not compulsory. It's mainly for the EBAHA we had focused. So yes. Yes, you will have to do a static presentation now. And you will be presenting the 5 dynamic scenarios that we talked about, which is the acceleration brake, on center, CRC, and steer step. So you will be following the same boundary conditions that we had set, which is the scenario and the maneuver commands. And you will be performing the simulation and you will be showing the results for your static presentation now. So all the guidelines, all the details will be mentioned in the guidelines, which is scheduled to release soon. Can we consider access system from center of ALC while modeling in IPG? Rhythm, can you take this question?
No, actually, you can't take the access system from ALC as the FR1 system is present at the rearmost vehicle for motion.
Okay, thanks, Rhythm. Yeah, so for the guidelines of HBAHA car maker, we will release it soon. So for now, you can refer the previous year HBAHA guidelines car maker and get started with modeling. So the powertrain parameters is basically your moment of inertia values is one of the main parameters that you mentioned for your differential shaft, output shaft, or other CVT the moment of inertia values at that place, and also the CVT ratios as well, and the transmission ratio and the uh, just a minute. Yeah. So you have so the efficiency that as well. So if you're having a very good efficiency, of course the resistance will be less. So the deadline for the presentation will be mentioned in the guideline. You will get ample of time to cover that. When will be getting Baha model? I didn't understand, Shreyas. So please clarify the question. Last time we had issue with importing the wheels model geometry. Please tell us in what aspect or context are you referring to? Is it SKC? Can you just clarify that, please? From Katia, how can we get, so Rhythm, you want to answer this?
Yeah, for each and every CAD softwares, there are different tools available. But the common tool is the coordinate system generation. By the help of that coordinate system, you need to create your own coordinate axis at the FR1 position.
Okay, thanks, Rhythm. The
I think so.
tracks.
So just one thing regarding the coordinate system. So I think so. Sandeep asked that question. So Sandeep, you can just I think you do a basic Google search and you'll get how can a coordinate system be reference coordinate system be created in CATIA on Google itself. There might be various tutorials also. Using that, you can create an FR1 coordinate system. I think so. We have covered it for Creo. I think so.
PO in SolidWorks, yes, we have
And
covered.
SolidWorks. For CATIA, I think so. You can just Google it and you can find it. And if you have any issues, I think well, I think yeah, it we can't help with CATIA because I think so. Yeah, it is uh, more about like you can just Google it and I think so you can find it out.
Will the tracks be provided? No. So you have to create the tracks, but yes, the track definitions, the scenarios, the length of the track, and the radius, everything will be mentioned in the guidelines, and that is what we also took you through in our sessions for each load cases. So if you can refer the video when you have it, and also the guidelines, you will be clear of how to create that scenario. So for the acceleration brake only, you have to build it from scratch. But for the other three scenarios, we will be using a product example track. So you don't actually have to build it from scratch everything.
Also, for ATP, Baha will be providing a track on which the teams need to do the lap time simulation. Right, Harish?
Yes, yes. So that track will be released much later, but the presentation around guidelines will be released, and the track definition for these 5 load cases will be released as well. So you can get started and work on optimizing your vehicle and the design. So we did cover this question that HM, you don't have exactly. Joe, do you want to answer this question? Sorry. Joe, are you there?
Hello, can you hear me?
Yeah, I can hear you. So the question
Yeah,
is that can we model HM? Yeah.
Yeah, the Hatcham actually you cannot build a nonlinear model with IPG as of now because they don't have a template for that yet. So for the Hatcham, you cannot use SKC or MBS. You have to use a linear 1 or 2D of model for that.
Okay, thanks, Joe. How can we import the self-designed tire model? So are you referring to renaming Raj, or are you referring if you have your own tire data? Please clarify. No, we don't have 7 events. We have 5. So 5 are the common ones for all the teams in all the categories. Apart from that, if you want to include any extra load case or scenario in your presentation, you are open to do that. So we only have 5. Okay, so if you have your own tire data, yes, you can explore that. You can rename any tire and you can open the tire file in Notepad and you can input that data. Or you can go through the tire generator app, tire generator, which is also present in CarMaker. You can refer the reference manuals for any clarification on that. No, the HBAHA powertrain is different for M&E. The values, the torque and power graphs are different. So you have to refer to the past year guideline that was released. But of course, we'll soon release the new updated guideline as well. So the PNG file you can ignore. you can use the OBJ file that the BAJA provides. You can generate the PNG file from that as well. So in the, okay, let me just share my screen. Yeah, my screen is visible, right? So, so let's say this is my body, right? So, uh, yeah, so we in BAJA we generally provide the OBJ general OBJ files. So this is only for visualization purpose. So this has nothing to do with your simulation or your vehicle design. So if you have the OBJ file from last year, you can just import it and you can just press on this gear icon, which will automatically generate the PNG file. So you don't have to build that PNG file from scratch. And this OBJ file, of course, we'll again release it in the upcoming Karmic, in the VDE Virtual Dynamic Event Guidelines as well. So the link will be provided there also, but you can refer from the past year guidelines also to get started. Yeah, go on.
For the FR1 coordinate, it is at the ground level that the FR1 is touching at the ground, but at the rearmost of the vehicle.
ATP and Manu. So you will only have ATP track for the simulation round. There will be no Manu event. So the ATP track, we will provide the track as well as the maneuver commands. So the maneuver commands, basically the maneuver parameterization for from the start to the end. You used to till last year you would give each driver like what the speed has to be till what distance or what time, right? Duration. So that also we will be giving along with the tracks. We will be releasing that, and it is common for all the teams. So the only variable is your vehicle model. To what extent you have optimized it using this virtual dynamic scenarios, and you are able to optimize and achieve the best lap time. You can use the OBJ file that is provided by BAJA. You don't have to use that. You don't have to spend time on building your own OBJ if you are having any issues. So it's only for visualization. It has nothing to do with your vehicle performance or anything, or any. It will not be considered for any evaluation per se. So the 5 dynamic events are acceleration, brake, on center, constant radius cornering test, and steer step.
Just one more thing regarding EJBA. So for EJBA, the guidelines isn't released yet. So the teams don't need to refer to MBA and EBA guidelines. It, for EJBA, the guidelines will be totally different. All the contents are like, I think the, especially the powertrain part is absolutely different. Okay,
Yes,
so
yes.
please don't refer MBA or EBA guidelines for EJBA. You need to refer to the last year's guidelines.
Yeah.
Okay, also, so you can find that on the forum, as well as we'll send a communication through Baha sharing the last year's guidelines.
Yeah. So the ATP track we will be releasing, and the maneuver for that ATP track we will be releasing, that you will be using for the simulation round. So the test run that you will be submitting, in that you will be using the maneuvers that we have provided and the ATP track that we have provided. Okay. Is it necessary to do range evaluation? No, it is not necessary. It is just for your understanding that you can find out your range for IBAHA is what we had covered. So if you are able to do it at your end, you can and show the optimization. You can include that in your presentation. There is no CVT model or any predefined model of CVT for IBAHA. Yeah. May I know for what reason you need a mentor or specialist for IPG only? So if you have any questions, you can post it on the forum or you can contact your alumni coordinators. They will reach out to us and we'll provide you the solutions along with the IPG team as well. We have so the content is what we had covered in the sessions that we were doing for the 5 virtual dynamic scenarios. The guidelines will also be released. So in that you will get more understanding of exactly what all you have to cover for each presentation or each slides that you can refer. But it's not compulsory to include all the data. You can include that. It's something minimum that you have to cover. Yeah. I don't know the data, sorry, the unit. You can refer the reference manual or do some research at your end to get that data. Thanks.
Yes, you can use any of the software to calculate moment of inertia. You just need to do is to enter the values in IPG.
Okay. Any questions regarding the scenarios that we had done for CRC, on center, and STSLab? Okay. Other resources you can refer to MathWorks website. There is MathWorks support as well, and there is MathWorks forum as well where you can post your queries and they can help you out if you have anything regarding battery modeling. Yeah. So I think yeah.
Sorry, Harish. So just one thing I'd like to add on the CVT point for eBaha. So for eBaha in IPG, there is no CVT model that is available. So for that, there are two options. One is using CarMaker for Simulink. So you'll need to do a co-simulation or you will need to create a like a C file and you need to link it to your car maker file or the vehicle file. And besides that, there is one more option is that if you don't want to do that thing, that is the most accurate one. And the other part is you can use AMT uh, for your powertrain if you're using CVT. For but this is just for E-bar teams. This is not at all for M-bar teams or H-bar teams. Yeah, Harish, continue.
Yeah. So as I mentioned before, the scenarios for the acceleration and brakes you have to create it, but you have to create it for the rest of the 3 scenarios. You can use the product examples, the road file which is present in the product example. So all that, what product example to use, and what should be the track dimension, everything we have covered today in this session. And also we will be replicating the same in the guidelines, which will be released soon. So yeah, so you can refer that and I'm sure your doubts will get clear.
Also, I think the guidelines will also mention what all things the teams can add in the presentation. Uh, and also the
Yes.
evaluation criteria of for the presentation round of virtual dynamic events will also be mentioned in the guidelines itself.
Yeah,
So I
and
think
the scoring format will also be there. What is the score distribution as well? Yeah, and can we import simulation data? Yeah, I mean, if you have built your, your points and you have done some KNC analysis in some other software, you can use the same points in IPG car maker, in IPG kinematics, and try to replicate the data. Of course, you will get the same results there as well. So yeah, but you can't directly import it. You have to go through the process that Joe had shown in his session, how to import single all the points one by one. And primary content is how you have optimized your vehicle, or the results that you are getting for each load case. So we have given you the load case definition. We have given you the scenario and the maneuvers, or the boundary conditions basically. Now you just have to perform that analysis at your end. You have to replicate that whole boundary conditions at your end, perform the analysis, and then get the results, the expected results that is required or asked, and show that in your presentation, like how well you have improved your vehicle from before and after comparison. Yeah. So I think that's all for today. I don't think there are any other questions. So once the guideline is released, most of your questions will get resolved. The entire recording of this meeting, yes, we will be sharing the recording. Tentative dates, it will be released soon. We will release the posters as well. You will get to know. Do you mean the kinematics, steering, suspension? If that is what you are meaning to, yeah, sure, you can go ahead.
But actually, the steering and suspension, you can use IPG kinematics for that. You don't have any other software access as of now. You can use IPG kinematics to get the out. As I have shown before, you can get all the toe, camber, caster, all the variables, how they are changing dynamically for your jumps, rebound. For in the IPG kinematics, using that, you can get everything in there.
Yeah, thanks, Jim. Yeah, I think that's all for today. So thank you so much, everyone. Thank you for joining. I hope this session had made a great impact on you. And I'm sure you are excited for the new challenge that we have put forth for this season of BAJA SAEINDIA 2025. And yeah, all the best for your presentations and the VDE event. You may take the leave now. Take your leave. Yeah. Thanks all.